Nobody survives interstellar travel, not with the bodies we currently have, not with the technology we currently possess. The honest answer to how long a human being would survive interstellar travel is not reassuring. It is not a number that inspires confidence. Your body would begin deteriorating within months. So before we even talk about the distance, how long does a human being actually last in interstellar space? If you love to stay awake at night thinking about questions like this, make sure to give this video a like. Now let's get started. Let us start not with distance, but with something far more unsettling: your DNA every single second of every single day. The cells in your body are being struck by something called galactic cosmic rays. These are not the cute, harmless rays of sunlight you picture when someone says radiation. Galactic cosmic rays are high-energy particles, some of them protons, some of them heavier atomic nuclei that have been accelerated across the galaxy by supernovae, by the violent deaths of stars, by events so catastrophic they release more energy in seconds than our sun will produce in its entire 10 billion-year lifetime. These particles travel at extraordinary fractions of the speed of, well, they travel extraordinarily fast, and they carry with them the memory of destruction. Right now, Earth's magnetic field deflects most of them. Our atmosphere absorbs a large portion of the rest. You are shielded in ways so profound and so invisible that you have never once had to think about them. In interstellar space, the vast, cold, dark nothing between star systems, that shield is gone. Scientists studying data from NASA's Lunar Reconnaissance Orbiter and from research conducted during the Mars Science Laboratory mission measured radiation levels in deep space and found something sobering. In a single year of interstellar level exposure, a human being would absorb a radiation dose many times greater than what is considered safe over an entire career as an astronaut in low Earth orbit. We are not talking about a slight increase in cancer risk. We are talking about the kind of cumulative cellular damage that rewrites the instruction manual your DNA uses to keep you alive. A 2-year mission to Mars and back, still well within our own solar system, still partially sheltered by the sun's magnetic bubble, the heliosphere, is already estimated to expose astronauts to radiation approaching the current safety limits set by space agencies. Now extend that journey to the nearest star system, Alpha Centauri, a triple-star system sitting roughly 41 trillion kilometers away. That is not a typo, 41 trillion. And it is our closest stellar neighbor, at the fastest speeds any human-made object has ever reached. And we are still not talking about anything remotely close to what would be needed. A journey to Alpha Centauri would take somewhere between 17,000 and 80,000 years. Your radiation exposure over that time would not just be lethal, it would be incomprehensibly, astronomically lethal. Every cell in your body would have been struck, damaged, repaired, damaged again, and broken beyond repair long before you ever saw that second sun on the horizon. But here is where it gets even more interesting. Radiation is only the beginning. There is a phenomenon that astronauts returning from long-duration missions on the International Space Station describe in ways that sound almost neurological. Their balance is off. Their vision has changed. Some of them describe a strange pressure, a heaviness behind their eyes. It is not imagined, it is not stress, it is a measurable, documented, physical change that happens to the human brain in microgravity. When you remove gravity from the equation, the fluids in your body redistribute. The cerebrospinal fluid, the liquid that normally flows around your brain and spinal cord, cushioning and protecting those structures, shifts toward your head. This is called spaceflight-associated neuroocular syndrome, and researchers at NASA have spent years trying to understand exactly what it does to human physiology over extended periods of time. What they have found is alarming. After just 6 months aboard the space station, a significant percentage of astronauts show measurable changes to the structure of their brains. The white matter shifts, the cerebrospinal fluid spaces enlarge, the optic nerves swell. Some astronauts return to Earth with permanently altered vision. And remember, the space station is only about 400 kilometers above your head. The astronauts up there are still very much inside Earth's magnetic protection. They still experience a form of gravity through their orbital motion. In true deep space, on an interstellar trajectory, you would be in genuine microgravity for years, decades, possibly generations. Your spine would lengthen, sometimes by as much as 7 centimeters, as the discs between your vertebrae expand without gravity compressing them. Your muscles, with nothing to work against, would begin to waste away at a rate of roughly 1 to 2% per month without aggressive intervention. Your bones would lose density in a similar pattern. The cardiovascular system, which evolved over millions of years to pump blood upward against gravity, would weaken as that demand disappears. Your heart would literally begin to shrink. A human being who spent 10 years in deep space without a rotating habitat providing artificial gravity would return, if they returned at all, essentially unable to stand. Their bone density would be that of someone with severe osteoporosis. Their muscles would be barely functional. Their vision might be permanently compromised. Now imagine not 10 years. Imagine 100, 1,000. Imagine the generations of people born on an interstellar vessel who have never once felt the pull of a planet beneath their feet. We have not even talked about the cold yet. The temperature of interstellar space, the actual ambient temperature of the void between stars, is roughly 2.7 degrees above absolute zero. In Celsius, that is negative 270.4 degrees. To put that in perspective, the coldest naturally occurring temperature ever recorded on Earth's surface was about negative 89.2 degrees Celsius in Antarctica. Interstellar space is roughly 3 times colder than that, not 3 degrees, 3 times. Any interstellar vessel would need to be hermetically sealed, perfectly insulated, and continuously heated. A breach of the hull, even a small one, caused by a micrometeorite impact or material fatigue, would not just be catastrophic, it would be almost instantly lethal. In the vacuum of space, liquids boil away, gases expand and escape. The human body, without a pressurized environment, would lose consciousness in roughly 15 seconds and be dead within about 90. And micrometeorites are not rare. In interstellar space, the density of dust and tiny particles is lower than inside a solar system, but the distances are so vast that even a low probability event becomes nearly certain over thousands of years. Over the course of a multi-generational voyage, the statistical certainty of hull impacts accumulates in ways that engineers find deeply uncomfortable to calculate, but let us set aside the physics for a moment. Let us talk about something even more fragile than bone or blood or skin. Let us talk about the mind. The longest continuous spaceflight ever recorded was achieved by the Russian cosmonaut Valery Polyakov, who spent 437 days, just over 14 months, aboard the Mir space station. He returned to Earth demonstrably changed, not broken, not defeated, but changed. He was one of the most psychologically resilient human beings ever selected for spaceflight, trained for years to endure isolation. And still, 14 months was enough to leave marks. Now consider what a genuine interstellar voyage would demand. Not 14 months, not 14 years, potentially 14 generations. The psychological literature on extreme isolation is harrowing. Human beings evolved in small, interdependent social groups with access to open horizons, changing seasons, natural light, and the constant sensory richness of a living world. Strip all of that away. Confine people to a sealed metal cylinder hurtling through a darkness so complete that the stars themselves would barely move for centuries. And what happens to the mind? Studies of Antarctic overwintering crews, submarine deployments, and simulated Mars missions like the CCAS Habitat project in Hawaii have all documented what researchers call the third quarter phenomenon. Roughly 3/4 of the way through any long-duration isolated mission, psychological distress spikes dramatically. Irritability, depression, interpersonal conflict, a loss of motivation so severe it has been compared clinically to a kind of existential shutdown, and those missions last months, not centuries. So here is the question that researchers, philosophers, and mission architects are genuinely grappling with. Is there a version of interstellar travel that the human mind, the human body, and the human soul could actually endure? The answer might surprise you, because scientists are not just theorizing, they are building, they are testing, and some of the solutions they are coming up with are stranger, more beautiful, and more unsettling than anything science fiction ever imagined. In the next part of this journey, we are going to look at what those solutions actually are. From generation ships to suspended animation to the radical idea of sending not people but something far more durable, and what that would mean for what it means to be human at all. But before we get there, consider this. Every element heavier than hydrogen in your body, the iron in your blood, the calcium in your bones, the oxygen filling your lungs right now, was forged inside a star that died before our sun was born. You are not traveling toward the stars. In the most literal, chemical, physical sense possible, you came from them. The real question is not whether we can survive the journey back. It is whether we are brave enough to try. There is something that happens the first time you look through a telescope at something genuinely, incomprehensibly far away. Not a photograph, not a screen. Your own eye, pressed against the eyepiece, receiving light that has traveled for millions of years to reach that precise point. Your retina, your mind. It is not a passive experience. Something shifts. If that feeling calls to you, there is one piece of equipment I personally keep coming back to, the Celestron StarSense Explorer. This telescope uses your smartphone to map the sky in real time and guides you, without any prior experience, directly to nebulae, planets, star clusters, and deep space objects. You do not need to know anything to begin, you just need to look up. I will leave a link to the telescope in the description and pinned on the comments. Now, let us go back to the darkness between stars. We ended in a place that was honest and a little heavy. The human body as it currently exists is not built for interstellar space. The radiation would accumulate, the muscles would waste, the bones would hollow, the mind would strain under pressures no psychological training has ever truly prepared anyone to face. And the distances involved are so staggering that even describing them in kilometers starts to feel almost meaningless, like trying to describe the depth of the ocean in teaspoons. But here is the thing about human beings. We have always been the species that refused to accept the limits of the environment we were born into. We were not built to survive the Arctic, and yet we settled it. We were not built to breathe underwater, and yet we mapped the ocean floor. We were not built to leave the atmosphere, and yet 12 human beings walked on the surface of another world. So when scientists, engineers, and mission architects sit down to seriously ask, how do we get a living human being across the light years, they do not stop at the problem. They start building solutions, and those solutions fall into roughly 4 categories, each one stranger and more philosophically loaded than the last. The first is the one that captures the imagination most immediately, the generation ship. The concept is elegant in its simplicity and terrifying in its implications. If the journey is too long for a single human lifetime, you do not send one generation, you send many. You build a vessel large enough to sustain a self-contained civilization, agriculture, medicine, governance, culture, reproduction, and you launch it knowing that the people who board it will never arrive. Their children will not arrive. Their grandchildren will not arrive. The people who finally set foot on a new world, perhaps 1,000 years after departure, will be the distant descendants of the original crew. People who were born in space, raised in space, and have never once seen a planet from the ground. This is not pure speculation. Researchers have modeled it extensively. A 2014 study published in the Proceedings of the National Academy of Sciences looked at minimum viable population sizes for multi-generational space travel. Their conclusion, and this is the part that tends to stop people cold, was that you would need a minimum of somewhere between 10,000 and 40,000 individuals to maintain sufficient genetic diversity, social stability, and functional redundancy over a multi-century voyage. A smaller group would accumulate genetic bottlenecks, social collapse, and civilizational fragility long before the journey ended. 10,000 people on a ship for potentially hundreds of years. The engineering challenge alone is almost incomprehensible. A vessel capable of carrying 10,000 people would need to be, by any reasonable estimate, on the scale of a small city. It would need closed-loop life support systems, recycling air, water and nutrients with near-perfect efficiency, because there is no resupply. No emergency landing, no turning back. If a critical system fails 100 years into the voyage, the people aboard cannot call anyone. The signal would take decades to arrive. The rescue mission, if one could even be mounted, would take centuries. The food system alone would require an area of agricultural land estimated at somewhere between 2 and 4 square kilometers of continuous, functional growing space to feed that population sustainably. And that food system would need to function for generations without access to new seed varieties, without the genetic diversity of Earth's agricultural ecosystem, and without the natural cycles of seasons and soil that human farming has depended on for 10,000 years. And then there is the question that the engineers do not always want to answer. What happens to the society? History does not offer many encouraging examples of isolated, closed populations maintaining cultural and institutional stability over centuries. Civilizations rise and collapse, governments shift, value systems erode or calcify into something unrecognizable. The people who depart Earth in Generation 1 will have a clear mission, a shared purpose, a living memory of the world they left behind. But by Generation 5, by Generation 10, that mission will be, for most people aboard, an abstract concept. A story, a religion, perhaps. The philosopher and anthropologist Catherine Denning, who has written seriously about multi-generational space travel ethics, raises a question that does not have a clean answer. Do we have the right to make that choice for people who do not yet exist? The children born on that ship never consented to the mission. They cannot leave. They cannot opt out. They will live and die inside a metal hull, in a darkness they may never fully understand, in service of a destination they will never reach. Some researchers describe it, without irony, as one of the most profound ethical dilemmas in the history of the species. Others argue that it is no different in principle from being born into any civilization on Earth, that none of us consented to the world we were born into, the values we were raised with, the limitations of the bodies we inhabit. But the generation ship removes every exit, every alternative, every horizon that is not steel and starlight. It is a closed world, and closed worlds across human history have a complicated relationship with freedom. The second solution is colder. Literally, suspended animation, sometimes called torpor in the scientific literature, is not science fiction anymore. It is not a solved problem either, but it is the subject of serious, funded research by serious institutions. The basic principle is this: if the journey takes too long for one human lifetime, you do not try to compress the journey. You slow the human down. The idea is to reduce the body's metabolic rate dramatically, dropping core temperature, slowing brain activity, suppressing the biological processes that cause aging, and maintain that state for years or decades without causing irreversible damage. When the ship arrives, you wake up. There is already a medical precedent, though a narrow one. In emergency medicine, therapeutic hypothermia is used to protect the brain during cardiac arrest and some surgical procedures. By lowering a patient's body temperature by just a few degrees, doctors can buy additional time before brain damage sets in. Some patients have survived cardiac arrest after being in a hypothermic state for periods that would normally be fatal. But the gap between therapeutic hypothermia lasting a few hours and suspended animation lasting decades is vast. The physiological challenges are profound. Ice crystal formation in cells can cause catastrophic damage at very low temperatures. The cardiovascular system needs to be maintained. The immune system needs to be suppressed without leaving the body vulnerable to opportunistic infections. And perhaps most critically, no one has yet demonstrated that a human being can be placed in true torpor and revived without measurable neurological damage. Spaceworks Engineering, a firm that has received funding from NASA's innovative Advanced Concepts program, has proposed a torpor system for a Mars mission that would keep crew members in a metabolically suppressed state for the majority of the journey, cycling through the crew so that someone is always awake to monitor systems, but keeping the overall physical and psychological load dramatically lower than a conventional mission. Their projections suggest that a torpor-based approach could reduce crew metabolic consumption and therefore food and water requirements by roughly 50 to 70%. That is not a small number. On a decades-long interstellar mission, that difference could be the line between survival and starvation, but the radiation problem does not go away during torpor. Your body is still being struck by galactic cosmic rays whether you are conscious or not. Your DNA is still accumulating damage. Some researchers actually argue that a torpid body might be more vulnerable, not less, because the active cellular repair mechanisms that normally respond to radiation damage are also suppressed along with everything else. So suspended animation is not a solution to interstellar travel. It might be a component of one. It might buy critical time. It might reduce the psychological toll, but it does not eliminate the fundamental hostility of the environment. The third solution is the one that makes biologists deeply uncomfortable and philosophers reach for their coffee: genetic engineering. If the human body as it currently exists cannot survive interstellar travel without extraordinary technological support, what if we changed the body? This is not a hypothetical anymore. The era of CRISPR-Cas9 gene editing has moved the possibility of targeted, inheritable genetic modification from science fiction into the domain of near-term science. We are not yet at a point where we can redesign a human being from the ground up, but the trajectory of the science suggests that within a century, possibly far less, we may have the tools to make targeted changes to the human germline that could, in principle, confer genuine biological advantages for space travel, enhanced DNA repair mechanisms, increased radiation resistance, reduced bone density loss in microgravity, altered circadian rhythms, even potentially modifications to the cardiovascular system that allow it to function more efficiently without the constant presence of gravity. NASA's Twin Study, a landmark investigation comparing astronaut Scott Kelly, who spent nearly a year aboard the International Space Station, with his identical twin brother Mark, who remained on Earth, revealed something extraordinary. After Scott's return, researchers found measurable changes in his gene expression. Certain genes involved in immune function, bone formation, and DNA repair had been switched on or off by the space environment in ways that persisted for months after his return. The space environment itself was altering how his genes behaved, not the underlying sequence, but the way those sequences were read and expressed. This field, epigenetics in space, is now one of the most active areas of research in human spaceflight biology. And what it suggests is fascinating. The body is not a fixed thing. It responds, it adapts. Perhaps, with sufficient time and sufficient scientific guidance, it could be made to adapt far more deliberately. But here is where the philosophy gets thorny. A human being modified at the genetic level to survive interstellar space, genuinely modified, not superficially. At what point are they still human? If you engineer someone to produce their own radiation-absorbing proteins, to need 60% less oxygen, to sleep for months without muscular atrophy, to experience social isolation without the cascading psychological collapse that isolation typically triggers, have you created a better version of a human, or have you created something new, something post-human? And if it is something post-human, does that change what it means for us to reach the stars? These are not rhetorical questions. They are the questions that researchers at the intersection of astrobiology, bioethics, and space medicine are actively, seriously debating. The journal Acta Astronautica has published multiple papers in recent years examining the ethical dimensions of human biological modification for long-duration spaceflight. The conversation is no longer happening only in philosophy departments. It is happening in labs, because the fourth solution, the one we have not talked about yet, might make all of this moot. What if we do not send humans at all? Not in the way you are probably thinking, not robots, not probes, not drones, something in between. Something that does not yet have a name that everyone agrees on, but which some of the most serious scientists in the world believe may be the only truly viable path to the stars. And to understand it, you need to understand something about what information actually is, what consciousness might be, and whether the thing that makes you is stored in your body or somewhere more fundamental. That is where we are going next, and I promise you, it is stranger and more beautiful than anything we have covered so far. The universe does not care about our biology, but it might have left us a door. Let us start with a question that sounds philosophical, but is actually deeply scientific. What are you? Not in the existential, late-night staring at the ceiling sense. In the literal, physical, information-theoretic sense, what is the thing that makes you you? The continuity of experience, the memory, the personality, the particular way you laugh at certain things and feel uneasy about others. Is that stored in your body, or is it stored in the pattern? Because if it is stored in the pattern, if consciousness, identity, and selfhood are fundamentally about the arrangement of information rather than the specific biological substrate carrying that information, then the question of interstellar survival changes completely, radically, almost beyond recognition. This is not a fringe idea. Some of the most rigorous thinkers in neuroscience, philosophy of mind, and theoretical physics take it seriously, and it sits at the heart of what may be the most honest answer science currently has to the question of how humanity reaches the stars. Let us build toward it carefully, because to understand where we might be going, you need to understand something about where the science of mind currently stands. The human brain contains roughly 86 billion neurons. Each of those neurons connects to thousands of others through structures called synapses. The total number of synaptic connections in a single human brain is estimated at somewhere around 100 trillion. The pattern of those connections, which ones are strong, which are weak, which fire together, which are silent, encodes everything you have ever learned, felt, remembered, or imagined. Your first memory, the sound of a voice you love, the particular quality of light on a specific afternoon that you cannot quite explain but have never forgotten. This pattern is called the connectum, and mapping it, understanding it with enough precision to read it, copy it, or reconstruct it, is one of the most ambitious scientific projects currently underway, the Human Connectome Project. launched with funding from the National Institutes of Health, has been working for over a decade to map the structural and functional connections of the human brain at increasing levels of resolution. In 2023, a team at Harvard and Google published the most detailed connector map ever produced, a cubic millimeter of human brain tissue containing roughly 57,000 cells and 149 million synaptic connections mapped at nanometer resolution. The data generated by that single cubic millimeter was approximately 1.4 petabytes. To put that in scale, that is roughly 1,400 terabytes of information. From a piece of brain tissue smaller than a grain of rice, the entire human brain at that resolution would generate data on a scale that currently exceeds our total global digital storage capacity by a significant margin, but storage capacity doubles, processing power grows. The history of computing is a history of the previously impossible becoming routine, and then cheap, and then invisible. So here is the idea that serious researchers are beginning to examine with serious tools. What if, instead of sending a biological human being across 41 trillion kilometers of lethal freezing, radiation-saturated void, you sent the pattern, a digital reconstruction of a human mind, a complete high-fidelity map of a person's connectome, their memories, their personality, their cognitive architecture, transmitted as a signal across interstellar space, not a copy of a person in the dismissive sense, the person, their information, their selfhood, translated into a format that travels at the fastest speed physics allows, at the destination, assuming a receiving station, a constructed habitat, perhaps a robotic infrastructure built by an earlier, faster probe. That pattern is instantiated, reconstructed, embodied, perhaps in a biological form grown from stored genetic material, or perhaps in a synthetic substrate, or perhaps in something we do not yet have words for. The person wakes up, not after thousands of years of radiation exposure and muscle atrophy and psychological disintegration, after a journey that, from their subjective perspective, may have lasted no time at all. This concept has several names in the literature: whole brain emulation, mind uploading, digital consciousness transfer, and it comes with a set of philosophical problems that make the generation ship ethics look straightforward by comparison. The most immediate problem is the one philosophers call the continuity of identity. If you perfectly copy every detail of your mind and transmit it across space, and then a reconstruction of you wakes up at Alpha Centauri, is that you? Or is it a copy of you while the original remains behind or ceases to exist at the moment of transmission? This is not a new puzzle. It is a version of the teleporter paradox that philosophers have wrestled with for decades. But the interstellar context gives it a weight that is hard to shake, because if the answer is that it is merely a copy, then what you have achieved is not interstellar travel. It is interstellar reproduction. The being that arrives at the destination shares all your memories, all your feelings, all your sense of self, but the thread of conscious experience that began when you were born was cut at the moment of transmission. The philosopher Derek Parfit spent a significant portion of his career examining questions exactly like this. His conclusion, deeply counterintuitive but rigorously argued, was that identity itself may be less important than we think, that what matters is psychological continuity and connectedness, that a being who remembers being you, who reasons as you reason, who values what you value, is, in every meaningful sense, a continuation of you, even if the physical substrate has changed entirely. Others disagree, profoundly, and the disagreement matters because if we ever build this technology, we will have to decide, not abstractly, concretely. We will have to decide what it means to send a person to the stars in this way, and whether the being that arrives deserves to be treated as the same individual who departed, with all the rights, relationships, and moral status that entails, But let us set philosophy aside for a moment and talk about something happening right now. Something real, funded and moving. In 2015, the Russian-Israeli billionaire Yuri Milner, together with the late Stephen Hawking and a coalition of scientists including the Nobel laureate Saul Perlmutter, announced a project called Breakthrough Starshot. The goal was straightforward in its ambition and staggering in its engineering challenge: send a probe to Alpha Centauri within a generation, not a large probe, not a crude vessel, a gram-scale wafer of electronics, a star chip, attached to a sail roughly 4 meters across, made of a material so thin it is measured in atoms. The sail would be accelerated by an array of ground-based lasers, delivering roughly 100 gigawatts of focused energy. Over the course of a few minutes, the tiny craft would be pushed to approximately 20% of the speed of light. At that velocity, the journey to Alpha Centauri would take roughly 20 years. 20 years, not 80,000. The challenges are immense. The laser array alone would require engineering breakthroughs that do not yet exist, and the starship would need to withstand interstellar dust impacts at a velocity where even a particle a fraction of a millimeter across hits with the energy of a small explosive. But the physics is real, the mathematics works, and the project has attracted serious scientific talent and over $100 million in funding. Breakthrough Starshot is not designed to carry humans. It is designed to carry sensors, cameras, instruments that might, if everything works, send back the first close-range images of another star system, fuzzy, distant, extraordinary images of a world that no human eye has ever seen. But the intellectual thread from Breakthrough Starshot to something more ambitious is not hard to follow. If you can send a gram-scale chip to another star in 20 years, what could you send in 50, in 100? As the technology advances, as miniaturization continues, as our understanding of information density grows, at what point does a chip become large enough to carry something more than sensors? At what point does it carry a mind? There is a researcher named Robert Freitas who has spent decades examining what he calls the theoretical limits of miniaturized, autonomous systems, machines small enough to work at the cellular or molecular level, intelligent enough to carry out complex tasks without external guidance. The concept he helped develop, nanomedicine, the idea of deploying microscopic machines inside the human body to repair damage, fight disease, and maintain health, has moved from pure theory into early-stage experimental reality in the decades since he first proposed it. Now extrapolate that idea to interstellar travel. Imagine a probe, not a gram, but perhaps a kilogram or 10, carrying the digital pattern of a human mind alongside a suite of molecular-scale manufacturing systems. The probe arrives at a destination after decades of travel. Its construction systems begin to work, drawing on local materials, rock, ice, organic compounds, to build a habitat, to grow biological structures from stored genetic templates, to reconstruct piece by piece the physical substrate necessary to instantiate the mind the probe has been carrying across the void. It sounds like science fiction. It is, currently, far beyond our engineering capability. But none of the individual components, digital mind mapping, molecular manufacturing, autonomous robotic construction, laser propulsion, violates any known law of physics. They are all engineering problems. Profoundly difficult engineering problems, yes, but engineering problems, not impossibilities. And that distinction matters enormously, because in the history of this species, the distance between profoundly difficult engineering problem and solved has consistently been shorter than anyone predicted. The Voyager probes, launched in 1977, are still functioning, still transmitting. Their power sources have lasted nearly half a century in the most hostile environment imaginable. Their designers, working with the computing technology of the mid-1970s, built something that has outlasted the careers of everyone who built it. Now imagine what engineers working with the technology of 2125 might build, or 2200, or 2500. The timescale of interstellar travel is not the timescale of a human life or a political administration. It is the timescale of civilization, and civilizations, when they are not busy destroying themselves, have a remarkable track record of achieving what previous generations thought impossible. But here is what sits beneath all of this, beneath the generation ships and the torpor chambers and the laser sails and the digital minds, and what no engineering solution fully addresses, the question of why. Why would we go? What would drive a civilization to commit resources on a generational scale, to accept losses and costs and ethical complications that dwarf anything in human history, to reach toward a star that offers no guaranteed welcome and no promise of survival? The cynical answer is resources, expansion, the same territorial imperative that drove human migration across continents and oceans, a species running out of room, looking for somewhere new to overflow into. But there is another answer, one that feels, to me, more honest curiosity, the same thing that made someone, tens of thousands of years ago, look at the horizon beyond the known world and take a step toward it. Not because they knew what was there, not because they had a plan, but because the not knowing was, somehow, unbearable in the most beautiful way imaginable. We are a species that asks questions, that names stars and maps galaxies and builds instruments of extraordinary delicacy to listen for whispers from the edge of the observable universe. We are, perhaps, the cosmos becoming aware of itself, matter that has organized into a form complex enough to look back at the processes that created it and say, I want to understand this, I want to go there, I want to know what is waiting in the dark. That impulse, ancient, irrational, irresistible, may be the most human thing about us, and it may be the thing that eventually carries us, in some form, across the void to the next star. But there is a shadow on all of this, a shadow that the most serious scientists in the field do not look away from, even when it is uncomfortable. What if we are not alone out there? Not in the comforting, optimistic sense of the question. In the other sense, what if the reason we have not detected any signals at all, from any other civilization in a galaxy containing hundreds of billions of stars and billions of years of cosmic history, is not because intelligence is rare? What if it is because the journey between stars is so lethal, so costly, so fundamentally at odds with the nature of biological life, that no civilization has ever successfully made it? What if the great silence of the cosmos is not an absence of life, but a graveyard of attempts? That question has a name. You may have heard it, the Fermi paradox, and in the next part of this journey, we are going to walk directly into it, because the Fermi paradox is not just a puzzle about alien civilizations. It is a mirror held up to our own. It is the universe asking us, very quietly, whether we are brave enough or wise enough to be the first ones through. The silence is vast, and the deeper you listen, the more it starts to sound like a warning. In the summer of 1950, the physicist Enrico Fermi sat down to lunch with a group of colleagues at Los Alamos National Laboratory. The conversation had turned, as conversations among physicists sometimes do, to the absurd and the cosmic, specifically to a recent rash of UFO reports in the newspapers and the light-hearted question of whether any of it could possibly be real. Fermi listened for a while, then asked a question so simple, so devastatingly precise, that it has echoed through scientific discourse for over 70 years. Where is everybody? That was it. 4 words. No elaborate equation, no complex theoretical framework, just a quiet, almost casual observation that if intelligent life is even remotely common in a galaxy this old and this large, we should have seen some sign of it by now, some signal, some structure, some artifact of a civilization that got here before we did, and yet nothing, silence, A cosmos that, despite containing hundreds of billions of stars, many of them billions of years older than our Sun, appears from every instrument we have ever pointed at the sky to be completely, utterly, and profoundly empty of anyone else. The paradox bearing Fermi's name is not really a paradox in the logical sense. It is a tension, a mismatch between what the mathematics of probabilities suggests should be out there and what observation actually finds. And the deeper astronomers look, the more sensitive our instruments become, the more exoplanets we catalogue, the more we understand about the conditions necessary for life, the sharper that tension becomes. Let us put some numbers to it, not to overwhelm, but to feel the weight of what the silence actually means. The Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. Based on data from the Kepler Space Telescope and its successor TESS, the Transiting Exoplanet Survey satellite, astronomers now estimate that the majority of those stars host planetary systems. A significant fraction of those systems contain planets in what researchers call the habitable zone, the orbital range, where liquid water could exist on a surface. Conservative estimates suggest there are somewhere between 8 billion and 40 billion potentially habitable Earth-sized planets in our galaxy alone, 8 billion. In one galaxy, of roughly 2 trillion galaxies in the observable universe, the universe is approximately 13.8 billion years old. Our Sun is about 4.6 billion years old. That means there are stars in this galaxy that are 9, 10, even 12 billion years old, stars that had time to form planetary systems, evolve complex chemistry, and potentially give rise to intelligent life billions of years before Earth even formed. If any civilization around any of those stars developed technology at even a fraction of the pace human civilization has, if any of them looked up at the sky and asked the same questions we are asking, they have had an almost incomprehensible head start. The physicist and astronomer Frank Drake formalized this thinking into what became known as the Drake equation in 1961, a formula designed not to give a precise answer but to organize the uncertainty, to lay out term by term the factors that determine how many communicating civilizations might exist in our galaxy right now. Depending on how you fill in the variables, and scientists disagree significantly on several of them, the answers range from less than 1 to millions. But here is the thing that cuts through all the uncertainty. If the answer is anywhere above 0, if even one other civilization has ever reached a technological level comparable to ours, anywhere in this galaxy, at any point in the last several billion years, the silence becomes very difficult to explain, because a sufficiently advanced civilization, with sufficient time, does not need to travel fast to fill a galaxy. It just needs to travel persistently. The mathematician and physicist John von Neumann described, in theoretical terms, a concept now called a von Neumann probe, a self-replicating machine capable of traveling to a new star system, using local materials to manufacture copies of itself, and sending those copies onward to the next system. The math of exponential growth means that even at a small fraction of the speed of light, a fleet of self-replicating probes launched from a single civilization could, in principle, explore or colonize every star system in the Milky Way within a few million years. A few million years sounds like a long time. On a human timescale, it is almost inconceivable, but on a cosmic timescale, in a galaxy that is over 13 billion years old, a few million years is an eye blink, less than 2% of the galaxy's current age. If any civilization capable of launching such probes has existed at any point in galactic history, the probes should be here by now, or the signals should be detectable, or the structures, the mega-engineering projects, the Dyson spheres, the organized patterns of energy use that would be visible across light years, should be showing up in our data. They are not, and that absence, that profound, consistent, unbroken silence, demands an explanation. The astronomer and astrobiologist Stephen Webb catalogued 50 possible explanations for the Fermi paradox in his book on the subject. They range from the mundane to the cosmic to the deeply unsettling. They are alive, but not yet communicating. They are communicating in ways we cannot detect. They are deliberately hiding. They are here, but observing without contact. In what some researchers call the zoo hypothesis, they exist, but only as simulations running inside a more fundamental computational substrate, what the philosopher Nick Bostrom outlined in his simulation argument. But there is one class of explanation that the astrobiologist and paleontologist Peter Ward, together with the astronomer Joe Kirschvink, brought into sharp scientific focus. An explanation that connects directly to everything we have been talking about in this video. An explanation that suggests the silence of the cosmos may not be a mystery about alien civilizations at all. It may be a message about us. It is called the Great Filter. The Great Filter, first articulated by the economist Robin Hanson in 1998, is a deceptively simple idea. Somewhere between dead matter and a civilization capable of spreading across the galaxy, there is a step, or possibly several steps, that almost nothing gets through. A filter so effective that it has, apparently, prevented any civilization in the observable universe from achieving a visible, galaxy-scale presence. The question that makes this idea genuinely terrifying is not whether the filter exists. Given the silence of the cosmos, most researchers accept that something is suppressing the emergence of visible civilizations. The question is, where is it? Is the Great Filter behind us? Has humanity already passed through the bottleneck that destroys most potential civilizations, the emergence of eukaryotic cells, the development of multicellular life, the appearance of complex nervous systems, and we are now on the far side of it, relatively rare survivors in a universe full of microbial dead ends? Or is the Great Filter ahead of us? Is there something waiting in the future? Something intrinsic to the development of technological civilization, or to the attempt to expand beyond a home world that consumes every species that reaches it? Something we are approaching right now without knowing exactly what it is or how close we are. The astrophysicist Adam Frank at the University of Rochester has studied the question of civilizational sustainability from an energy and climate perspective, arguing that the emergence of an industrial civilization may almost inevitably trigger planetary-scale environmental changes that the civilization must learn to navigate or perish. His research suggests that the critical transition from a planet-bound civilization to a genuinely spacefaring one may be where most civilizations fail, not through war or accident, through the slower catastrophe of a species that consumes its homeworld's resources faster than it can develop the capability to leave. If that is true, if the Great Filter is the gap between a technological civilization and a spacefaring one, then humanity is currently inside it. And here is where the interstellar survival question and the Fermi paradox converge in a way that is, depending on your temperament, either deeply sobering or powerfully motivating. Every challenge we have discussed in this video, the radiation, the bone loss, the psychological collapse, the impossibility of life support over multi-generational timescales, the ethical abyss of generation ships, the speculative leap of digital consciousness, every one of those challenges is part of what makes the transition from a planetary civilization to a genuinely interstellar one so extraordinarily difficult. And if every civilization that has ever existed has faced those same challenges, if the biology of carbon-based life is similarly fragile across the cosmos, if the distances are just as vast for everyone, if the physics does not make exceptions for intelligence or ambition or good intentions, then the silence of the cosmos starts to look less like an absence of life and more like a universal testimony to the difficulty of the crossing. The void between stars may be the most consistent, most democratic, most indiscriminate barrier in the history of the universe. It does not care how smart you are. It does not care how motivated you are. It does not care about your technology, your culture, your philosophical frameworks, or your survival instinct. It simply presents its conditions: radiation, cold, distance, time, isolation, and it waits to see what survives. Most things apparently do not. But let us be careful here, because the great filter hypothesis, as haunting as it is not the only serious framework for understanding the silence, and some of the alternatives are, in their own way, almost as unsettling. The astrobiologist Caleb Scharf, director of astrobiology at Columbia University, has proposed what he calls the Gaian bottleneck hypothesis, developed in collaboration with the researcher Aditya Chopra. The idea is that life itself may be extraordinarily common in early planetary history, but that maintaining a habitable environment over the billions of years required for intelligent life to evolve is extraordinarily rare. Most planets, they argue, start with the right conditions but cannot sustain them. Venus and Mars may both have had liquid water in their early histories. Venus is now a sulfuric acid hell with surface temperatures hot enough to melt lead. Mars is a frozen desert with an atmosphere so thin it offers almost no radiation protection. Earth, by contrast, has maintained a relatively stable climate for roughly 3.5 billion years, long enough for single-celled life to evolve into complex multicellular organisms, for complex organisms to evolve nervous systems, for nervous systems to evolve into brains capable of asking questions about the universe. That stability was not guaranteed. It was, according to Scharf and Chopra, the product of an extraordinary series of feedback loops, biological, geological, and astronomical, that kept our planet in the narrow band of conditions life requires for long enough to produce us. The Moon, for instance, stabilizes Earth's axial tilt. Without it, our planet's axis would wobble chaotically over millions of years, producing climate swings too extreme for complex life to persist. Jupiter's gravitational field acts as a partial shield against the most destructive cometary impacts. The position of our solar system within the galaxy, not too close to the violent, radiation-saturated galactic center, not so far out that heavy element chemistry is sparse, may itself be a condition that relatively few planetary systems share. We may live on a rare world, a world whose very stability was in some profound sense lucky. And if that is true, if stable, complex life-bearing worlds are genuinely rare, then the universe may be full of the ruins of civilizations that never quite made it far enough to leave. Planets where life arose, where intelligence emerged, where cities were built and questions were asked, and telescopes were pointed at the stars, and where, for one reason or another, the crossing to the next star never happened, where the great filter, whatever form it took, was never passed. That is not a comfortable thought. It was not meant to be. But here is the thing about uncomfortable thoughts. The best ones are the ones that change how you see, that make the ground feel different under your feet, that turn an ordinary Tuesday into something slightly more weighted, more significant, more worth paying attention to. Because if we are rare, if this civilization, this world, this improbable thread of conscious experience that runs from the first cell to this exact moment, is genuinely unusual in the cosmos, then what we do with it matters in a way that is hard to fully articulate but impossible to dismiss. The silence of the universe may not be telling us we are alone. It may be telling us we are early, that we are among the first to reach this particular threshold, that the choices we make now about sustainability, about cooperation, about whether we develop the wisdom to match our technology, may echo across millions of years of cosmic history in ways we cannot predict and will never fully see. There is a version of this story that ends in wonder, where humanity, having faced every physical and psychological challenge the void between stars presents, finds a way through, where the generation ships launch, where the torpor chambers open at journey's end, where the digital minds wake in unfamiliar light and look up at an alien sky and feel, despite everything, at home. There is another version that ends in silence, another civilization, another signal, another attempt that the cosmos absorbs without comment. Which version we inhabit depends, in ways that are uncomfortably specific and uncomfortably near, on decisions being made right now, in laboratories, in governments, in the quiet choices of individuals who look up at the night sky and decide whether what they feel in that moment is worth acting on. But whichever version we are in, and I genuinely do not know, and I do not think anyone does, there is something happening right now in the science of interstellar travel that neither version fully accounts for. Something practical. Something being built and tested and argued over in real institutions with real funding and real engineers who go home at night and think about the problem and come back the next morning and try again. Something that may represent the most realistic, near-term path toward the stars that our civilization has ever produced. We have talked about what would kill us out there. We have talked about the silence that might be waiting. Now it is time to talk about the actual, concrete, funded, peer-reviewed attempts to solve those problems, one by one, system by system, organ by organ, if necessary, because the engineers are not waiting for the philosophers to finish their argument. They are already building. There is a building at the Johnson Space Center in Houston where people spend their days figuring out how to keep human beings alive in places that want to kill them. Not dramatically, not with explosions and crisis alarms, quietly, methodically, with spreadsheets and tissue samples and pressure gauges and an almost monastic dedication to the unglamorous reality that space exploration, at its most fundamental level, is a life support problem. How do you keep a fragile biological organism, an organism that evolved on a warm, wet, magnetically shielded world with a thick atmosphere and a reliable supply of food and social contact, alive and functional in an environment that offers none of those things for months, for years, for generations? That question, which sounds like it belongs in a science fiction novel, is the subject of serious, funded, peer-reviewed research happening right now. And the answers being developed are not the clean, sleek solutions of the movies. They are messy, complex, deeply human attempts to engineer around the limitations of biology that millions of years of evolution never anticipated. Let us start with the most fundamental one: gravity, the bone loss, the muscle atrophy, the cardiovascular weakening, the cerebrospinal fluid shifts that alter brain structure and damage vision. Every one of these effects traces back, in whole or in large part, to the absence of the one force your body has been calibrated against since the first moment of your existence. Gravity is not just a physical phenomenon for a human being, it is a developmental signal, a constant, continuous input that your entire physiology uses to organize itself, to decide how dense your bones need to be, how strong your muscles need to be, how hard your heart needs to work. Roam it and the body does not hold its shape. It drifts. It reorganizes around a new set of demands that evolution never wrote instructions for. The most extensively studied solution is artificial gravity through rotation. The concept is straightforward. Spin a section of the spacecraft fast enough, and the centrifugal force experienced by the people inside mimics the effect of gravity. The faster the rotation and the larger the radius, the closer the simulation to what we experience on Earth's surface. This is not a new idea. It appeared in the work of the rocket pioneer Konstantin Tsiolkovsky in the early 20th century. It was depicted with extraordinary accuracy in Stanley Kubrick's 2001, the rotating space station that produces artificial gravity through centrifugal force. and it has been studied seriously by aerospace engineers for decades. The challenge is engineering a habitat large enough to provide comfortable artificial gravity at a rotation rate slow enough that the human vestibular system does not rebel, because rotate too fast, and you get a nauseating mismatch between what your inner ear feels and what your eyes see, needs to be very large. Estimates vary depending on the target gravity level and acceptable rotation rate, but a habitat providing one full gravity, equivalent at a rotation rate, low enough for comfortable habitation, would need a radius of somewhere between 200 and 900 meters. That is an enormous structure to launch, assemble, and maintain in deep space. But here is what has changed in the last decade. The economics and engineering of large space structures have shifted dramatically. The development of heavy-lift launch vehicles, SpaceX's Starship being the most prominent current example, has begun to make the assembly of large orbital and deep space structures more plausible than they have ever been, and advances in materials science, particularly in the development of high-strength, low-mass structural materials, are steadily reducing the mass penalty of building large. The centrifuge concept has never been closer to buildable than it is right now, and several serious mission architecture proposals for Mars and beyond have incorporated rotating habitat sections as a baseline assumption rather than a speculative luxury. But artificial gravity, as essential as it is, addresses only one branch of the survival problem. The radiation branch is in many ways the harder one, and the solutions being developed for it are some of the most creative pieces of engineering in current aerospace research. The primary challenge with radiation shielding is mass. The traditional approach, surrounding a habitat with dense material like lead or polyethylene, works, but the mass required to provide meaningful shielding against galactic cosmic rays is so large that it makes the spacecraft impossibly heavy with current or near-future propulsion systems. A shield thick enough to reduce cosmic ray exposure to acceptable levels using passive mass shielding alone might require hundreds of tons of material per square meter of habitat surface. For a ship large enough to carry a crew, the total shielding mass would exceed anything a realistic propulsion system could accelerate to the velocities needed for interstellar travel. So engineers are looking at active shielding, and this is where the physics gets genuinely exciting. The principle comes from observing how Earth protects us. Our planet does not stop radiation with a thick wall of dense material, it deflects it with a magnetic field. The magnetosphere, generated by the motion of molten iron in Earth's outer core, creates a vast, invisible bubble around our planet that curves the paths of incoming charged particles, redirecting them away from the surface or channeling them toward the poles where they produce the auroras. If you could generate a strong enough magnetic field around a spacecraft, a miniature magnetosphere, you could in principle replicate this effect. Incoming cosmic ray protons and heavy ions, being electrically charged, would curve around the field lines rather than punching through the hull. The European Space Agency and several university research groups have been developing what they call the mini-magnetosphere concept for over a decade. Early theoretical work, supported by laboratory plasma experiments, has confirmed that the basic physics is sound. A superconducting coil generating a field of sufficient strength could deflect a significant fraction of the incoming charged particle radiation that would otherwise irradiate a crew. The remaining challenge is the neutral particles, neutrons and gamma rays, which are not deflected by magnetic fields because they carry no electric charge. For those, a combination of hydrogen-rich material shielding, water is actually an excellent neutron moderator, which is one reason why some mission architects propose using the spacecraft's water supply as part of the shielding structure, and carefully designed habitat geometry can reduce exposure to more manageable levels. No single solution eliminates the radiation problem entirely, but the combination of active magnetic shielding for charged particles, water and polyethylene shielding for neutrons, careful habitat positioning within the spacecraft's existing structure, and pharmacological interventions, drugs that enhance the body's DNA repair mechanisms and reduce oxidative stress, may, together, bring radiation exposure down to levels that are dangerous but survivable over multi-year missions. Whether they can bring it down to acceptable levels over a multi-decade or multi-century voyage is a different question, and honest researchers will tell you that the answer remains genuinely uncertain. Let us talk about air and water and food, because before you worry about the stars, you need to worry about lunch. Every human being consumes roughly 500 liters of oxygen per day through respiration. They exhale roughly 400 liters of carbon dioxide. They drink between 2 and 3 liters of water. They consume somewhere between 1.5 and 3 kilograms of food. They produce waste, solid and liquid, that contains resources recoverable through processing and resources that are simply lost to the system. On the International Space Station, these flows are managed through a combination of stored supplies, regularly resupplied by cargo missions, and a partially closed-loop life support system that recovers water from humidity, condensation, and urine through filtration and electrolysis. The current system on the space station recovers roughly 90% of the water used by the crew. The remaining 10% represents a genuine loss that must be resupplied from Earth. For a mission that cannot be resupplied, ever, 90% is not good enough, not remotely. On a voyage lasting decades or centuries, even a fraction of a percent of daily resource loss, compounded over time, eventually empties the tank. NASA's Environmental Control and Life Support System Research Program has been working for years toward what engineers call a fully closed-loop system, one that recovers and recycles 100% of water, regenerates oxygen continuously from carbon dioxide, and processes waste into usable nutrients with negligible loss. The current state of the art is impressive, but not there yet. The gap between 90% recovery and 100% recovery is, in engineering terms, significant. Every additional percentage point requires increasingly sophisticated and reliable processing systems. And reliability is the word that keeps every life support engineer up at night. A system that works 99% of the time is a system that fails roughly 3.5 days per year. On a 50-year mission, that is over 6 months of failures. Some of those failures will be minor, some will cascade. Some in a sufficiently critical system, oxygen generation, water purification, atmospheric pressure maintenance, will be fatal. The engineering principle that addresses this is redundancy. Every critical system needs a backup. Every backup needs a backup. And every component needs to be maintainable and repairable by the crew using materials and tools that can themselves be manufactured or replenished aboard the ship. This is why several serious interstellar mission concepts have proposed incorporating three-dimensional printing capabilities, additive manufacturing as a core life support technology, the ability to fabricate replacement components on demand from raw feedstock rather than specific pre-made parts dramatically increases the resilience of the system. You do not need to carry every possible spare part. You need to carry the raw materials and the manufacturing capability to make them when they are needed. Food is its own extraordinary challenge. The caloric requirements of a crew of 10,000 people over a century represent an agricultural enterprise comparable to a small nation. The crops need to grow in artificial light because there is no sun to speak of, or if there is one, it is the wrong one, in hydroponic or aeroponic systems that use water and nutrients with maximum efficiency. The genetic diversity of the crop species needs to be maintained across generations to prevent the kind of catastrophic vulnerability that comes from monoculture farming, the agricultural equivalent of a genetic bottleneck. And the nutritional completeness of the diet needs to be maintained not just for one generation, but for the many that follow. Without access to the vast diversity of Earth's food ecosystems, vitamin deficiencies, mineral imbalances, the effects of eating a nutritionally adequate but monotonous diet for decades on both physical health and psychological well-being are areas where the science is still developing. Some researchers have proposed incorporating cultured meat, protein grown from cell cultures rather than whole animals, as a more resource-efficient protein source than conventional livestock. Others have looked at insect farming, which converts organic waste into protein with extraordinary efficiency compared to conventional agriculture. Algae cultivation, particularly spirulina and chlorella, offers the dual benefit of producing both food and oxygen through photosynthesis. Each of these technologies works to varying degrees in laboratory and small-scale settings, scaling them to the demands of a multi-generational crew, maintaining them reliably across centuries, and integrating them into a coherent food ecosystem that meets every nutritional requirement without external input. That is the challenge that no one has yet solved, but people are working on it. Seriously. Right now, there is one more survival system that rarely gets the attention it deserves in discussions of interstellar travel, one that is at least as critical as oxygen or water or food, and far more difficult to engineer: medicine. A crew isolated in interstellar space has no access to hospitals, no specialists, no pharmaceutical supply chains, no surgical suites beyond what they carry. If someone develops appendicitis 2 light-years from Earth, a condition that is straightforwardly treatable with a procedure that takes about an hour in a modern hospital, the options available to them are entirely dependent on the medical capability of the ship they are aboard. And appendicitis is one of the simpler problems: cancer, organ failure, complicated childbirth, traumatic injury, stroke, dental emergencies, which are surprisingly common in astronauts and surprisingly debilitating if untreated, psychiatric crises, addiction. The full spectrum of human medical need does not pause because you are between the stars. The research response to this challenge has taken several directions. Telemedicine and artificial intelligence-assisted diagnosis have advanced significantly. Systems that can analyze symptoms, imaging, and biological data and provide treatment recommendations without a human physician in the loop are already in clinical testing for remote medicine applications. The idea of an AI medical system capable of guiding a non-specialist through complex procedures in real time is not science fiction. It is a near-term engineering goal. The pharmaceutical challenge is harder. Drugs degrade. Different drugs degrade at different rates, and the radiation environment of interstellar space may accelerate that process in ways not yet fully characterized. Maintaining a pharmaceutical supply across decades or centuries may require onboard synthesis capability, the ability to manufacture drugs from precursor chemicals rather than storing finished products. And then there is the biological dimension that no pharmaceutical can fully address: the human immune system, in the absence of the rich microbial ecosystem of a planetary environment, may itself become a problem. Research on long-duration spaceflight has documented changes in immune function. Some immune responses become dysregulated. Some pathogens that are normally suppressed by a healthy microbiome become more problematic in the confined recycled air environment of a spacecraft. Maintaining the diversity of the human gut microbiome, the community of microorganisms that lives in your digestive system and plays critical roles in immune regulation, mental health, and metabolic function, across generations in a closed environment is a research area that has only recently begun to receive serious attention. What happens to the microbiome of people born and raised in space, never exposed to the vast microbial diversity of a planetary ecosystem? We genuinely do not know. And that uncertainty represents one of the more quietly alarming gaps in our understanding of long-duration human spaceflight. All of these challenges, gravity, radiation, life support, food, medicine, microbiome, share a common feature that makes them collectively more difficult than any one of them alone. They interact. A radiation event that damages the intestinal lining compromises nutrient absorption, which affects muscular and bone health, which increases injury risk, which stresses the medical system, which affects crew morale, which has knock-on effects on the social and psychological health of the ship's population. A crop failure that reduces caloric intake increases physical stress, which affects immune function, which increases susceptibility to pathogens that the confined environment circulates efficiently. A psychological crisis in a senior technical crew member cascades into reduced maintenance quality, which increases the risk of system failures, which creates new crises. The ship is a system, a living system, and living systems fail in ways that are rarely linear, rarely predictable, and rarely confined to the domain where they begin. This is why some of the most serious thinking about interstellar mission architecture has come not from aerospace engineers or biologists alone, but from systems scientists, researchers who specialize in understanding how complex, interdependent systems behave under stress. The Santa Fe Institute, which studies complexity science across disciplines, has contributed frameworks for thinking about the resilience and failure modes of closed, long-duration human habitats that are beginning to influence how mission architects think about the problem. The conclusion those frameworks tend to reach is both reassuring and sobering in equal measure. Reassuring because complex systems that are well-designed, well-maintained, and inhabited by people with a genuine sense of shared purpose and mutual investment have remarkable resilience. They absorb shocks, they adapt, they find solutions that their designers never anticipated. Sobering because complex systems that lose that sense of shared purpose, that fragment socially, that develop internal conflicts about resources or governance or values, can collapse with startling speed. And the history of isolated human communities on Earth, from Antarctic expeditions to long-duration submarine deployments to isolated island settlements, suggests that maintaining social cohesion under extreme prolonged stress is in many ways the hardest engineering problem of all, because you cannot engineer human nature. You can only work with it. And that brings us back, after all this engineering, to the most stubbornly human question of all. What would it actually feel like? Not the systems, not the numbers, not the failure modes. What would it feel like to be a person alive on that ship, born there perhaps, knowing no other sky, looking out through a viewport at a darkness so vast and so absolute that the stars themselves barely move from one decade to the next? What would home mean to someone who has never had one that was not made of metal and recycled air? What would nature mean? What would it mean to grow old in a place where the horizon is always the same distance away, where the seasons are artificial, where the rain is a scheduled mist from a pipe in the ceiling? And what would it mean? What would it feel like to be the generation that finally sees it, the one that watches through that same viewport as a point of light that has been growing imperceptibly brighter for decades finally resolves into something recognizable? A disk, a color, a sun that is not your sun, but is close enough to cast shadows, close enough to feel warm, close enough to remind your body of something it has never experienced, but somehow genetically remembers. That moment, if it ever comes, will be one of the most significant in the history of life on Earth. perhaps in the history of life in this part of the galaxy, and it will be experienced by people who never asked to be part of it, who were born into the mission the way we are all born into the civilizations that shaped us, without consent, without choice, carrying a purpose given to them by people they never met, toward a destination they were told was worth it. Whether it will be worth it is a question only they will be able to answer. But here is what I find extraordinary, standing here on this side of the crossing, the fact that we are asking the question at all. The fact that a species that spent most of its history unable to survive a winter without fire is now seriously, rigorously, scientifically planning how to cross the void between stars. That is not a small thing. That is one of the most remarkable facts about the universe that I am aware of. We are matter that has learned to ask where it came from and to point itself deliberately back toward the source. That impulse, ancient and stubborn and gloriously impractical, has never once, in the entire history of this species, led us backward, and I do not think it will now. But there is something we have not yet addressed. Something that changes the entire calculation in ways that researchers are only beginning to fully understand. What if the greatest threat to an interstellar crew is not the void outside the ship, but the biology inside it? What happens across generations to the human genome itself in the radiation environment of deep space? What changes accumulate in the DNA of children born between the stars? Children whose parents were born there, whose grandparents were born there. And at what point do those accumulated changes produce something that is, in any biologically meaningful sense, no longer quite what it was when the journey began? That question leads somewhere that is either deeply hopeful or deeply troubling, depending on how you look at it. And that is exactly where we are going next. If you are enjoying this journey, make sure to subscribe and give this video a like. What you get in return is a front row seat to the cosmos every single time we release something new. Every living thing on Earth is the product of mutation. That is not a dramatic overstatement. It is a precise biological fact. Every adaptation that has ever allowed a species to survive a changing environment, every new enzyme, every modified receptor, every structural protein that made a bone stronger or an eye sharper or a nervous system more complex, began as a copying error, a mistake in the replication of a strand of DNA that turned out by chance to be useful. That got passed on, that compounded across generations into something that, eventually, we call evolution. The process is slow, glacially, almost incomprehensibly slow on a human timescale. The mutations that distinguish you from your great-great-grandparents are vanishingly rare and almost certainly trivial. Evolution works across thousands of generations, not 4 or 5, but in interstellar space, something changes, the mutation rate changes. And when you understand what that means, what it actually implies for the bodies of people living and reproducing across multiple generations in a radiation environment, orders of magnitude more intense than anything evolution ever prepared us for, the question of what arrives at the destination becomes genuinely, fascinatingly, unsettlingly open. Let us be precise about the biology, because the details matter here. DNA replication is not perfect. Every time a cell divides, every time your body makes a new copy of itself, which it is doing constantly, approximately 37 trillion cells maintaining themselves across a lifetime, there is a small probability of an error, a wrong nucleotide inserted, a deletion, a duplication. Under normal conditions on Earth, the rate of these spontaneous mutations is extraordinarily low, roughly 1 error per 10 billion base pairs replicated. Your body also has extraordinarily sophisticated repair mechanisms, enzymes that patrol the genome, identify mismatches and damage, and correct them before they propagate. Ionizing radiation disrupts this system. High-energy particles passing through cellular nuclei break DNA strands directly, Sometimes single-strand breaks that the repair machinery can handle, sometimes double-strand breaks that are far more difficult to repair correctly and far more likely to produce permanent mutations if they occur in a germ cell, a sperm or egg cell, that goes on to contribute to the next generation. The data from Hiroshima and Nagasaki survivor studies, from Chernobyl area research, and from occupational radiation exposure studies all document elevated mutation rates in populations with chronic radiation exposure. The increases are measurable. They are not always immediately catastrophic. The body's repair systems are remarkably good at catching and correcting even radiation-induced damage, but they are real and they accumulate. In the radiation environment of interstellar space, outside the heliosphere, beyond any stellar magnetic protection, the dose rate is significantly higher than anything studied in those terrestrial contexts. The particles are more energetic. The heavy ions that make up a significant fraction of galactic cosmic rays are particularly effective at causing clustered DNA damage, multiple breaks and lesions in close proximity, that is much harder for repair enzymes to handle correctly than isolated single-point damage. Over one generation, the elevated mutation rate is a serious medical concern, but not necessarily a civilizational one. Over 10 generations, over 100, the mathematics of accumulating heritable mutations in a small, closed population becomes a genuinely different kind of problem. In evolutionary biology, there is a concept called Müller's Ratchet, named after the geneticist Hermann Müller, who described it in 1964. The idea is this: in a small, asexually reproducing population, or even a sexually reproducing population with limited genetic diversity, deleterious mutations accumulate over time in a way that is difficult to reverse. Each generation inherits the mutations of the previous one and adds new ones. The ratchet clicks forward. It rarely, if ever, clicks back. In a large population with extensive genetic diversity, natural selection is efficient. Individuals carrying harmful mutations are less likely to reproduce successfully, and those mutations tend to be purged from the population over time. But in a small, isolated population, exactly the kind of population that an interstellar vessel would carry, the efficiency of selection drops dramatically. Chance plays a larger role. Genetic drift, the random fluctuation of gene frequencies in a small population, can cause harmful mutations to spread simply because the individuals carrying them happened, by chance, to reproduce more, not because those mutations were beneficial. Just because statistics in small samples are noisy, the combination of elevated mutation rate and reduced selective efficiency in a small, isolated population is, in genetic terms, a scenario that evolutionary biologists find quite uncomfortable. It is a scenario associated in the fossil record and in conservation biology with population decline and eventual extinction, not the flourishing of a healthy, adapting lineage. Some researchers have proposed genetic screening and intervention as a management strategy, regularly assessing the genomic health of the population, identifying and potentially correcting harmful accumulated mutations using gene editing tools. This is technically plausible in principle. CRISPR-Cas9 and its successors have already demonstrated the ability to correct specific disease-causing mutations in human cells. A sufficiently advanced version of that technology, applied systematically across a breeding population, could in principle counteract the worst effects of radiation-induced genetic drift. But this raises an immediate and profound ethical question. Who decides which mutations are harmful? Who controls the genetic destiny of an entire isolated population? The history of human attempts to manage population genetics, eugenics programs of the 20th century, is one of the darkest chapters in modern history. The idea of deploying genetic management on an interstellar generation ship even with the best intentions and the most sophisticated tools, sits in territory that ethicists approach with extreme caution. But here is the other side of the coin, the one that is, depending on your perspective, either hopeful or deeply strange. Not all mutations are harmful, and in a genuinely novel environment, an environment as different from Earth as the interior of an interstellar spacecraft is, some mutations that would be neutral or mildly disadvantageous on Earth might, in this new context, be quietly advantageous. Consider a mutation that slightly reduces the efficiency of vitamin D synthesis would be a mild disadvantage on a sun-drenched savanna. Inside a spacecraft lit by artificial full-spectrum lighting at controlled, consistent intensities, it might be completely irrelevant. A mutation affecting the regulation of bone density, reducing the hormonal signals that trigger bone remodeling in response to mechanical load, would be damaging on Earth, where you need bones strong enough to carry your weight. In microgravity, or in a partial gravity environment provided by rotation, the selection pressure on bone density is simply different. Over many generations, the accumulated mutations of a population living in space would not just represent degradation, they would represent adaptation, drift in directions that the environment of the ship, rather than the environment of Earth, was shaping slowly, imperfectly, in ways impossible to predict in advance. The people who arrived at the destination, if they arrived, would not just be psychologically and culturally different from the people who departed. They might be measurably, documentably, biologically different, not in dramatic science fiction ways, not pointed ears and extra lung capacity, but in subtle, real, statistically significant ways: different average height, different metabolic rates, different immune response profiles, different sensory thresholds, different hormonal regulation patterns. They would be, in the most literal biological sense, a new variety of human being, shaped by a journey rather than by a world. And at the destination, if there is a habitable world waiting, they would face the extraordinary challenge of readapting to conditions their bodies had spent generations moving away from. Gravity again, a real sun with a different spectral profile than the one their lighting systems had been mimicking, a microbial environment entirely unlike anything their immune systems had ever encountered, atmospheric chemistry, air pressure, humidity, temperature, all potentially different from both Earth and from the controlled interior of the ship they had always known. The first generation to walk on that new world would be, in a very real sense, as alien to it as it was to them. There is a concept in astrobiology called panspermia, the hypothesis that life can travel between worlds carried on rocks ejected by asteroid impacts, surviving the journey through space and seeding new planets when they land. The evidence for panspermia is not conclusive, but it is not negligible. Certain bacteria, Deinococcus radiodurans being the most famous example, are extraordinarily radiation resistant, capable of surviving doses thousands of times what would kill a human being. Dormant spores have been recovered from ancient materials and successfully revived. The basic biology of life, at its most stripped down, is more durable than our everyday experience of it might suggest. But what interstellar travel implies for a human population is something more than panspermia. It is directed, intentional, technological evolution, a species deliberately placing itself in conditions that will change it, knowing that it will change, accepting that the beings at the journey's end will be different from the beings at the beginning, and choosing to make that crossing anyway. That is, in the history of life on Earth, genuinely unprecedented. Life has always been shaped by its environment passively. It goes somewhere new and adapts. It does not choose to go somewhere that will transform it, with full awareness of what the transformation might entail. We would be the first species, as far as we know, to make that choice consciously. Now let us zoom out, further than we have gone in this video so far, because there is a perspective on all of this, on the radiation, the mutations, the generational change, the biological drift that shifts everything. A perspective that comes not from biology or engineering, but from the deepest timescales of astrophysics. The universe is approximately 13.8 billion years old. Life on Earth has existed for roughly 3.5 billion of those years. Complex animal life, the kind with nervous systems and mobility and something resembling behavior, has existed for perhaps 600 million years. Homo sapiens, in our current anatomical form, has existed for roughly 300,000 years. Anatomically modern humans, 300,000 years. The agricultural revolution, the development of settled civilization, writing, mathematics, the entire accumulated infrastructure of human knowledge is roughly 10,000 years old. The Industrial Revolution is about 250 years old. The space age is 68 years old. We are, by any cosmic measure, extraordinarily new, and yet in those 68 years, in the single human lifetime that has elapsed since the first artificial satellite crossed the sky, we have landed on the moon, sent probes to every planet in the solar system, detected gravitational waves from colliding black holes a billion light-years away, imaged the event horizon of a supermassive black hole, discovered thousands of exoplanets, and begun to seriously engineer the tools that might one day carry us to them. The acceleration of that curve is, when you sit with it, almost vertiginous. If you extrapolate even modestly, if you assume that the pace of scientific and technological development continues at something like its current rate for another few centuries, the civilization that exists in 300 years will be as incomprehensible to us as our current civilization would be to a person from the year 1700. The tools they will have, the knowledge they will carry, the things they will consider obvious that we currently consider impossible, and that 300-year civilization will be the one that actually launches the first serious interstellar mission. Not us, not our children, perhaps not even our grandchildren, but the inheritors of the trajectory we are currently on, people shaped by everything we discover and build and understand between now and then. The question of whether we could survive interstellar travel is, in this longer view, partly the wrong question. The right question might be, what version of us will eventually make the attempt, and will it still be recognizably us? The physicist and futurist Freeman Dyson, one of the most creative and rigorous scientific thinkers of the 20th century, spent decades imagining the deep future of intelligent life in the cosmos. He proposed megastructures, interstellar arcs, civilizations operating on astronomical timescales, but one idea he returned to repeatedly was more intimate than the megastructures, more personal. He imagined a kind of deep-time optimism, a conviction that the universe, for all its hostility and scale and indifference, was structured in ways that allowed for complexity to persist and grow, that the arrow of time in a cosmos cooling and expanding from its fiery origin pointed toward increasing structure and organization rather than away from it, that life, this improbable, stubborn, endlessly inventive phenomenon, had properties that aligned with the universe's tendency to produce interesting things in interesting places. He was not naive about the challenges. He understood the physics. He understood the distances. He understood that the universe offers no guarantees and makes no accommodations for ambition. But he also understood something that the data, honestly examined, supports. Life is older than we thought, more widespread than we suspected, more chemically flexible than any single example suggests, and intelligence, whatever it is, whatever gives rise to the particular quality of awareness that sits behind your eyes right now and follows these words and wonders, may be a more natural outgrowth of sufficiently complex chemistry than we have yet allowed ourselves to believe. We may not be a fluke. We may be, in some deep structural sense, what the universe does when it has enough time and the right ingredients. And if that is true, if intelligence is a natural product of a universe that is structured the way ours is, then the silence of the cosmos becomes less a graveyard and more a waiting room, full of civilizations that have not yet reached the threshold, full of life that has not yet learned to ask where the stars go, full of beings, perhaps, who will one day look up from their own worlds and see our signal, however faint, however strange, and know they are not the only ones. But before we get too comfortable in that hope, there is something we need to confront directly, something that the study of deep space travel makes unavoidable. The universe has a timeline, and it is not infinitely forgiving. Stars die, galaxies evolve. The window during which the cosmos supports the kind of chemistry that produces life, the stelliferous era, astronomers call it, the age of stars, is finite. We are currently about halfway through it. In roughly 5 billion years, our sun will exhaust its hydrogen fuel, expand into a red giant, and sterilize the inner solar system. In 100 trillion years, a timeframe so vast it barely registers as a number, the last red dwarf stars will flicker out, and the universe will enter a long, dark, increasingly cold epoch in which the conditions for life as we understand it will no longer exist anywhere. That is the frame. That is the context in which the question of interstellar survival sits. Not just, can we cross to the next star, but, over the full available window of cosmic time, what is possible? What could a civilization that survives its own technological adolescence eventually become? What could it see? What could it understand? What could it touch and build and be? The physicist Lee Smolin has argued that the universe may be, in some deep sense, a self-reproducing system, that black holes give rise to new universes with slightly varied physical constants, and that the constants of our universe are, in a meaningful sense, selected for the ability to produce black holes and therefore complexity and therefore life. If that is true, we are not passengers in an indifferent cosmos. We are, in some strange and recursive way, part of how the universe perpetuates and understands itself. That is either a deeply beautiful idea or a deeply unsettling one, possibly both. Here is what I keep coming back to after everything. The human body is not built for interstellar space. That is simply true. The radiation would accumulate. The gravity would be wrong. The isolation would strain every psychological architecture evolution gave us. The distances are so vast they make the word vast feel inadequate, and yet the human body is also not built for the Arctic, or the deep ocean, or the upper atmosphere, or the conditions inside a nuclear reactor, or the sterile, pressure-controlled environment of a surgical suite, or the vacuum that exists on the other side of the wall of the space station, where people are right now, living and working and sleeping and occasionally looking out the window at the curve of the world below them. We built our way into all of those environments. We built the tools, the knowledge, the systems, and the cultural infrastructure that made the impossible merely difficult and the merely difficult eventually routine. The question is not whether interstellar travel will be possible for a human civilization that survives long enough to develop the necessary tools. Given the trajectory of the science, given the pace of biological and material and computational knowledge growth, given the depth of the human impulse to cross every horizon that presents itself, the question is whether we will survive long enough to get there. And that question is perhaps the most important one any civilization has ever faced, because the stars are patient. They have been waiting for billions of years. They will wait a little longer. The question is whether we will. In the next part of this journey, we are going to look at something that most interstellar travel discussions skip entirely, something that sits not in the future, but in the present. The psychological and philosophical work, the inner preparation, the cultural readiness, the shift in self-understanding that a civilization needs to make before it can seriously undertake the crossing. Because the greatest barrier to the stars may not be engineering, it may not be biology, it may not even be distance, it may be imagination, the willingness to think on a timescale that dwarfs any individual life, to act for descendants who will never know your name, to invest in a future so far away it feels, from the inside, almost like myth. That shift, from a civilization that thinks in years to one that thinks in millennia, may be the most critical transition we have not yet made, and the universe characteristically offers no instructions for how to make it. There is a cathedral in Cologne, Germany, that took 632 years to build. The foundation stone was laid in 1248. The building was not completed until 1880. Dozens of generations of architects, stonecutters, laborers, and clergy worked on a structure that none of them would live to see finished. The people who laid the first stones knew, with absolute certainty, that they would die long before the spires rose. The people who raised those spires had never met the people who dug the foundations. They were separated by centuries of history, plague, war, and social transformation so profound that the world of 1248 was almost unrecognizable to the world of 1880. And yet the cathedral was finished, not because any individual persisted long enough to complete it, but because the idea persisted, because each generation understood itself as a link in a chain that extended backward into a past it had not witnessed and forward into a future it would not inhabit. Because the meaning of the project was larger than any single human life, and people found that enlargement, that participation in something genuinely vast, worth the investment of their finite time and energy. If humanity ever launches an interstellar mission, it will be the Cologne Cathedral of civilizations. And the question of whether we are psychologically and culturally capable of that kind of commitment is not a minor footnote to the engineering challenges. It may be the central one. The psychologist and systems thinker Joanna Macy spent decades studying what she called the problem of deep time, the difficulty human minds have in genuinely engaging with timescales that exceed a single lifetime. Her research and the work of researchers who built on it converged on a striking conclusion. The human brain is not naturally equipped to feel the future the way it feels the present. We can reason about the distant future. We can construct intellectual models of it, but we do not feel it, not with the same urgency, the same emotional reality, the same motivating force that the immediate present commands. This is not a moral failing, it is a cognitive architecture. The neural systems that generate motivation evolved to respond to immediate threats and immediate rewards, predators, food, shelter, social connection. They were not designed by evolution to respond with equal urgency to events that will unfold over centuries. The result is a systematic bias, documented across cultures and contexts, toward decisions that favor the near term over the long term, toward investments that pay off within a lifetime over investments that pay off across generations. The economists call it temporal discounting. The further away in time a reward is, the less value we assign to it, even when the logic of the situation clearly indicates that the future reward is larger and more important. Studies have shown that people will consistently choose a smaller reward available immediately over a larger reward available in the future, even when they consciously understand that the future reward is the better choice. Now apply that cognitive architecture to the question of an interstellar mission. The investment is immediate. The resources required, financial, scientific, industrial, social, political, would be drawn from the present, from living people with immediate needs and competing priorities. The payoff, The arrival at another star system, the expansion of the human presence beyond our solar system, is centuries or millennia away. No one alive at the time of the launch will see the destination. No one who will see the destination will remember the launch. For a civilization governed by electoral cycles measured in years and economic planning horizons measured in quarters, this is not just a practical challenge. It is a structural incompatibility between the timescale of the project and the timescale of the institutions that would need to fund and sustain it. The question is whether that incompatibility can be overcome, and history, when you look at it carefully, suggests that it sometimes can. The pyramids of Giza were constructed over a period of roughly 80 years, involving a workforce estimated in the tens of thousands, sustained across multiple pharaonic reigns, drawing on agricultural surpluses and organizational complexity that required generations of institutional development to accumulate. The people who began quarrying the limestone for the Great Pyramid did not live to see its completion. The civilizational commitment that made it possible was not a single decision but a cultural framework, a set of shared beliefs about the meaning of death, continuity, and divine order that made the investment feel not just worthwhile but necessary. The medieval cathedrals of Europe operated on a similar principle. The Apollo program, condensed into a single decade by the particular pressures of Cold War competition, demonstrated that democratic societies under sufficient motivation could sustain extraordinarily expensive, technically demanding long-term projects even without the structures of authoritarian coordination. And the Large Hadron Collider at CERN, a 27-kilometer ring of superconducting magnets buried beneath the French-Swiss border, built by a collaboration of over 10,000 scientists from more than 100 countries over roughly 30 years at a cost of several billion euros, shows that international scientific cooperation can sustain projects of civilizational ambition even in the absence of a single political authority driving them. What these examples share is not just commitment. They share something more specific, a narrative, a story that the people involved could tell themselves and each other about why the sacrifice was worthwhile, why the investment of finite human time and energy into something larger than any individual life was an act not of futility but of meaning. For the cathedrals, the narrative was theological. For the pyramids, it was cosmological and dynastic. For Apollo, it was nationalistic and exploratory in roughly equal measure. For the Large Hadron Collider, it is the purest form of the scientific narrative, the belief that understanding the fundamental structure of reality is worth doing for its own sake, regardless of immediate practical application. An interstellar mission would need its own narrative, one powerful enough and true enough to sustain commitment across centuries, across political upheavals and economic crises and cultural shifts that no one can predict, across the generations of people who will be born into the project without choosing it and who will need to find, in their inherited participation, something worth caring about. What would that narrative be? Some researchers and philosophers have proposed that the narrative already exists, that it has existed in fragmentary form for as long as human beings have looked up at the night sky and felt that particular combination of smallness and longing that the stars reliably produce. The narrative is this: we are the universe becoming aware of itself. We are matter organized into a form complex enough to ask where it came from and curious enough to want to go back. The exploration of space, and ultimately the crossing to other stars, is not an externally imposed project, but the natural expression of what conscious, intelligent life does when it reaches a sufficient level of development. It looks outward, it reaches, it goes. This narrative has the advantage of being, in a meaningful sense, scientifically grounded. The atoms in your body were forged in stellar interiors. The carbon in your DNA was synthesized in the nuclear furnaces of stars that lived and died before our sun was born. The iron in your blood was scattered across space by the explosive deaths of massive stars, supernovae, whose remnants are still expanding through the galaxy today. You are, in the most literal chemical sense, made of the cosmos looking at itself, and the desire to return to that cosmos, to cross the void and touch another star's light, is not a fantasy imposed on nature from the outside. It is, perhaps, what nature does with itself when it gets the chance. That is a narrative worth sustaining, worth building institutions around, worth teaching to children who will teach it to their children, across the centuries that separate the first stone from the finished spire. But narratives alone are not enough. The cathedral needed architects, engineers, quarrymen, supply chains, political and economic systems stable enough to sustain the work across generations of social change. The story gave people a reason to show up. The institutions gave them a way to coordinate once they did. An interstellar mission would require institutions of a kind and durability that human civilization has not yet developed. Institutions capable of maintaining a coherent purpose and organizational structure across centuries, of surviving the inevitable political upheavals, economic crises, and cultural shifts that history suggests will occur on any timescale longer than a few decades. Of making binding decisions for people who do not yet exist, about a mission those people did not choose. The philosopher and political theorist Edmund Burke described society as a partnership between the dead, the living, and the yet-to-be-born. Most of our political and legal institutions, however, are designed primarily to serve the living. The dead have already made their contribution. The yet-to-be-born have no vote, no legal standing, no mechanism for expressing their interests in decisions being made on their behalf today. This is what some legal scholars and political philosophers call the problem of intergenerational justice, and it becomes acutely, uncomfortably concrete in the context of an interstellar mission. The decision to launch would be made by living people, specific individuals in specific institutions at a specific historical moment. The consequences of that decision, the lives lived aboard the vessel, the culture that develops, the biological and psychological changes that accumulate, would be experienced by people who had no part in making it. People born into a mission the way the rest of us are born into nations, religions, and economic systems, without consent, without alternatives. Is that ethical? The philosopher David Bunin has argued that the comparison to ordinary birth, where none of us consent to the world we are born into, is relevant but imperfect. The difference, he suggests, is not that the generation ship removes choice where ordinary life provides it. Both situations involve people born into circumstances they did not choose. The difference is the severity and the totality of the constraints. A person born on Earth has horizons, alternatives, the possibility, even if not the guarantee, of moving, changing, leaving the circumstances they were born into. A person born on an interstellar vessel has no horizon that is not the one the ship provides. Whether that difference is morally decisive, whether it makes the generation ship fundamentally unethical rather than merely difficult, is a question that serious philosophers disagree on, sometimes sharply, and it is a question that will need an answer before any civilization can proceed with moral seriousness. There is another dimension to the inner preparation for interstellar travel that rarely gets discussed in the technical literature, but is, in a practical sense, at least as important as the engineering grief. An interstellar mission is, among other things, an act of departure on a scale that makes every previous human departure look local. The people who board that vessel, or whose ancestors boarded it, if we are talking about a mission launched generations before our own time, are leaving not just a place but an entire world, the only world human life has ever known. every ecosystem, every mountain range, every ocean, every sunrise, every familiar smell of rain on warm earth, all of it permanently, unreachably behind them. The psychological literature on grief is rich and nuanced. It documents, with considerable precision, what happens to human beings who lose something deeply and irrevocably. The stages are not linear, the timescale is not predictable, and the loss of a world, not a person, not a home, but an entire planet, an entire sky, the entirety of the natural and cultural context in which human psychology evolved, would be a form of grief without precedent, without cultural template, without any existing framework for processing it. Studies of immigrants and refugees, people who have left their home countries permanently under conditions of conflict or desperation, document elevated rates of depression, anxiety, and a condition called cultural bereavement, a complex form of grief specifically associated with the loss of cultural context. Not just the physical place, but the language, the social norms, the sensory environment, the particular texture of daily life that tells a person who they are and where they belong. Now scale that experience to the permanent, irreversible loss of an entire planet. The first generation aboard an interstellar vessel would carry that grief in ways that their children and grandchildren would not, because their children would not know what they had lost in the same visceral, embodied way, but the children would inherit the emotional residue, the stories, the longing encoded in cultural memory for a world their parents described and they have never seen, a form of collective homesickness for a home that no one currently alive has ever visited. Some anthropologists who study diaspora communities, communities defined by their separation from an original homeland, see parallels that are instructive rather than comforting. Diaspora cultures have a remarkable capacity to preserve identity and coherence over centuries of geographical separation from the origin point. Jewish cultural identity persisted across 2,000 years of diaspora before the establishment of Israel. The Irish cultural identity that shaped communities across North America, Australia, and beyond remained recognizable and vital for generations after the original emigration. The connection to an origin point, even one that no living member of the community has ever seen, can be a source of profound cultural cohesion and motivational force. An interstellar crew might draw on exactly this mechanism. Earth, the origin point, impossibly distant, growing dimmer with every passing year, might become not a source of paralyzing grief, but a source of identity. The thing they came from, the reason they exist, the context that gives the mission meaning, not because they can return to it, but precisely because they cannot. And then there is the question of what happens when that context is finally, irrevocably too distant to matter. At some point on a multi-century voyage, perhaps at the halfway point, perhaps earlier, the signal delay between the ship and Earth would become so extreme that real-time communication would be impossible. A message sent from the ship would take years to arrive. The reply would take years to return. Conversations would stretch across decades. News from Earth would arrive so delayed as to be historical record rather than current event. At some point, Earth itself would become, to the people aboard, something closer to mythology than geography. A story about where they came from, a light so faint in the aft viewport that it was no longer distinguishable from the other stars. What happens to a civilization when it loses its origin point, when the anchor that connected it to the larger human story frays and eventually parts? Some researchers argue that it would be catastrophic, that the loss of connection to Earth would produce a civilizational crisis of identity and purpose that could destabilize the social cohesion necessary to complete the mission. Others argue the opposite, that the moment the ship becomes genuinely self-contained, genuinely its own world, with its own history and its own future, and no meaningful connection to a past it cannot reach, may be the moment its inhabitants finally fully commit to what they are. Not travelers, not exiles, not passengers on someone else's mission, a people. With a destination, there is a concept in navigation called dead reckoning. Before the development of GPS, before radio positioning systems, before the precise astronomical instruments of the modern era, sailors crossing open ocean would determine their position by tracking their known starting point, their speed, their heading, and the time elapsed since departure. No external reference, no landmarks, just a careful, continuous accounting of where they had been and how they had moved, from which they inferred where they were. It required extraordinary discipline. A single uncorrected error, a miscalculated current, a logged speed slightly off, a heading drifted by a degree, would compound over days and weeks into a position error large enough to miss an island entirely. To sail past a destination in the darkness without ever knowing it was there. But the sailors who were good at it, who had the patience and precision and intellectual honesty to maintain their reckoning faithfully across the featureless expanse of an open ocean, arrived where they intended to arrive. They trusted the process. They trusted the mathematics. They trusted the continuous, unspectacular discipline of knowing where you are because you have kept careful track of everywhere you have been. An interstellar civilization will need that same discipline, not in navigation, though precise navigation across light years is its own formidable challenge, but in purpose. The discipline of knowing why you are going where you are going, of maintaining that knowledge faithfully across the generations that will pass between departure and arrival, of not letting the reckoning drift, because a mission that loses its purpose in the middle of the void, a generation ship whose inhabitants forget or reject or reimagine the goal that launched them, does not simply fail to arrive. It becomes something else entirely. A closed world adrift, a civilization without a destination, a people defined by movement but no longer by direction. Whether that is a catastrophe or a liberation probably depends on who you ask. But here is the thing about all of this inner work, all of this philosophical and psychological and cultural preparation that I find most worth sitting with. We are already doing it, not for an interstellar mission, not yet, not consciously, not in any coordinated way. But the cultural and philosophical shifts that would need to precede a genuine commitment to interstellar travel are already underway, in fragmentary and sometimes barely visible ways, in the work of astronomers and philosophers and writers and engineers who spend their days thinking about timescales that exceed any individual life. The development of long-term thinking as a recognized intellectual discipline through institutions like the Long Now Foundation, through the growing field of existential risk research, through the work of philosophers who argue that the interests of future generations deserve the same moral weight as the interests of present ones, is creating, slowly and imperfectly, the cultural infrastructure that deep time commitments require, the growth of a genuine global scientific culture, one that crosses national and linguistic and political boundaries, that maintains its commitments across generations of researchers, that values understanding for its own sake on timescales that dwarf any individual career, is demonstrating in practice that human institutions can sustain long-horizon projects with coherence and purpose, and the particular, irreplaceable experience of looking up at the night sky and feeling something, that ancient, wordless, physically felt response to the scale and beauty of the cosmos, is still happening, still pulling people out of doors on clear nights, still making children ask questions that adults cannot answer, still doing whatever it is that it has always done to the particular kind of creature that we are. That experience is not preparation for interstellar travel in any engineering sense. but it may be the deepest preparation of all, the one that happens not in laboratories or institutions but in individual minds, in the moment when the distance becomes real and the silence becomes meaningful and the stars stop being decoration and start being destinations. That moment happens to people every day, everywhere on Earth, under every sky, and every time it does, something shifts. Something that is very old and very stubborn and very much alive in us turns, however slightly, toward the dark between the stars and takes, however slightly, a step. But there is something we have been circling this entire time, something that waits at the intersection of all these threads, the biology, the engineering, the psychology, the philosophy, the cosmic silence, and demands to be addressed directly. What if none of it matters the way we think it does? What if the frame we have been using, the idea of a journey, a departure, a crossing, an arrival, is itself the wrong frame? What if the universe, in its characteristic way of being simultaneously more hostile and more generous than expected, has structured things so that the crossing we imagine is not the crossing that will actually happen? What if the real interstellar journey does not look like anything we have described? What if it looks like something we do not yet have the concepts to describe, and the science to imagine it is already quietly being done? That is where we are going next, into the genuinely speculative but rigorously grounded frontier of interstellar travel concepts that break every intuition we have brought to this conversation so far. Warp drives that may not violate physics after all, wormholes that some serious theorists believe the universe may have produced in abundance, and the extraordinary, humbling possibility that the cosmos itself, not our engineering, not our biology, not our philosophy, may have already provided the road. We just have not learned to read the map yet. If the physics we are about to discuss makes you want to see the cosmos yourself, make sure to check out the Celestron StarSense Explorer. IRT finds any object in the sky automatically, no experience needed, just curiosity. The link is in the description and pinned on the comments. We have spent a while of this journey talking about the problem of interstellar travel as though the universe is a fixed, passive arena, a vast, cold, empty stage across which we must somehow drag ourselves, biology intact, across distances that mock every scale of measurement we possess. We have talked about radiation and bone loss and psychological collapse and genetic drift and the philosophical weight of committing generations of unborn people to a mission they never chose. All of that is real. All of it is grounded in the best science currently available, but there is another conversation happening in theoretical physics, a quieter one conducted mostly in the language of tensor calculus and differential geometry, in papers that most people never read and that most scientists approach with a mixture of genuine excitement and extreme caution, a conversation about whether the universe itself, the fabric of space-time that everything we have ever known or measured or touched exists within, might offer possibilities that our engineering intuitions have not yet accounted for. And the answer, from some of the most rigorous theoretical physicists working today, is deeply, carefully, cautiously, maybe. Let us start with the idea that has captured the public imagination most completely, and that the physics treats with the most complex mixture of promise and skepticism. The warp drive. In 1994, the Mexican physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity that described in mathematically precise terms a solution to Einstein's field equations, the equations that govern the behavior of space-time itself, that would allow a region of space to move faster than light relative to the surrounding universe, while the interior of that region remained perfectly flat, perfectly normal. A bubble of ordinary space-time carried along by the expansion of space behind it and the contraction of space ahead of it, Like a surfer carried by a wave, the occupants of the bubble would experience no acceleration, no time dilation in the usual sense, no violation of the local speed of light. Inside the bubble, nothing moves faster than light relative to its immediate surroundings. The bubble itself simply moves, carried by the geometry of space-time rather than by any conventional propulsion. On paper, in the mathematics, it works. The Alcubierre metric is a valid solution to Einstein's equations. It does not obviously break any fundamental law of physics in the way that, say, sending information backward in time does. The problems, however, are considerable. The first and most immediately devastating is the energy requirement. Early calculations suggested that maintaining an Alcubierre warp bubble large enough to contain a spacecraft would require an amount of negative energy, a form of energy with properties opposite to normal matter and energy, which does exist in quantum mechanics, but in vanishingly small amounts, comparable to the total mass energy of Jupiter, or, in some formulations, larger than the observable universe. That is not an engineering challenge, that is a fundamental barrier, but the story did not end there. Because physicists characteristically kept working on the mathematics, and in 2012, the physicist Harold White at NASA's Johnson Space Center published a revised analysis suggesting that by modifying the geometry of the warp bubble, making it thicker and oscillating the intensity of the field, the exotic energy requirement could be reduced by many orders of magnitude, not to something buildable with current technology, but to something that at least did not immediately require the mass energy of a gas giant. White's team subsequently set up a small laboratory experiment, the White-Jude warp field interferometer, to look for any measurable distortion of space-time produced by a ring of capacitors arranged in the geometry his calculations suggested. The results were inconclusive. The distortions measured, if they were real signal rather than noise, were at the very edge of the instrument's sensitivity. No one claimed a breakthrough. But no one abandoned the mathematics either. Then, in 2021, something genuinely interesting happened. A team led by the physicist Eric Lentz at the University of Göttingen published a paper describing a new class of warp drive solutions, what he called soliton solutions, that, unlike the Alcubierre metric, did not require exotic negative energy at all. The energy required was still enormous by any practical standard, equivalent to the mass energy of a large planet, converted entirely to the specific form needed. But it was positive energy, normal energy, the kind the universe actually contains. The paper was peer-reviewed, it was taken seriously. It did not claim that warp drives were imminent or even probable, but it opened a door that the exotic energy requirement had previously kept firmly closed. The possibility that faster-than-light travel, or something functionally equivalent to it, might be achievable in principle without invoking physics that has never been observed. The wormhole is a different story, and in some ways a more grounded one. Wormholes, formerly called Einstein-Rosen bridges, have been part of general relativity since 1935, when Albert Einstein and his collaborator Nathan Rosen derived them as a mathematical consequence of the equations Einstein had published 20 years earlier. The basic structure is a tunnel in space-time connecting two distant regions, potentially regions separated by billions of light years, through a shortcut that passes through a higher dimensional geometry rather than across the conventional space between them. For most of the following decades, wormholes were treated as mathematical curiosities rather than physical objects. They were unstable, collapsing faster than any signal or object could traverse them, and they seemed to require the same exotic negative energy as the Alcubierre drive to be held open. But in 1988, the physicist Kip Thorne, who would later share the Nobel Prize for the detection of gravitational waves, and his colleagues Michael Morris and Ulvi Yurtseva published a paper in Physical Review Letters specifically designed to answer the question of whether a traversable wormhole, one that a human being could actually pass through, was consistent with known physics. They were doing it at the request of Carl Sagan, who wanted to know whether the faster-than-light travel in his novel Contact was physically defensible. Their conclusion was carefully qualified but genuinely remarkable. A traversable wormhole was not obviously ruled out by general relativity. It would require exotic matter to stabilize. But the Casimir effect, a real, experimentally measured quantum mechanical phenomenon in which two closely spaced metal plates in a vacuum experience a measurable attractive force due to the suppression of virtual particle fluctuations between them, demonstrates that negative energy densities can exist, at least locally and briefly, in the real universe. Whether Casimir-type negative energy could be harnessed and scaled to the degree required to stabilize a macroscopic traversable wormhole is a question that remains at present unanswered. The gap between the tiny, transient negative energy densities observed in Casimir experiments and the sustained macroscopic negative energy a wormhole would require is vast, but vast is not the same as infinite. And in the decades since Thorne's paper, the theoretical understanding of traversable wormholes has developed considerably. In 2017, the theoretical physicists Juan Maldacena and Leonard Susskind proposed something that has since become one of the most discussed ideas in fundamental physics. A conjecture, now known by its shorthand ER equals EPR, that suggests a deep and previously unsuspected equivalence between two phenomena that had seemed completely unrelated. R refers to Einstein-Rosen bridges, wormholes. EPR refers to Einstein-Podolsky-Rosen, the famous 1935 paper describing quantum entanglement, the phenomenon in which two particles, once they have interacted, remain correlated regardless of the distance between them. Measuring one instantly affects the other, no matter how far apart they are. Maldacena and Susskind proposed that these two phenomena, wormholes and quantum entanglement, are not separate things. They are the same thing, described in different languages. That every pair of entangled particles is in some deep geometric sense connected by a microscopic wormhole. That the non-local correlations of quantum mechanics and the non-local geometry of general relativity are aspects of a single underlying structure. If that is correct, and it remains a conjecture, not a proven theorem, though it is taken very seriously, then wormholes are not exotic, rare, artificially constructed things. They are woven into the fabric of reality at the quantum level. The universe is, in some sense, threaded with them. What that means for macroscopic traversability, whether the quantum-scale wormholes implied by entanglement can ever be scaled up, amplified, or made usable for actual transport, is a question that current physics cannot answer. But the question is no longer purely speculative. It is connected to the deepest and most active frontier of theoretical physics, where quantum mechanics and general relativity are being slowly, painfully, brilliantly reconciled. There is a third concept that deserves attention here, one that is less dramatic than warp drives or wormholes, but perhaps more immediately relevant to the question we started with, laser sails. We mentioned the breakthrough Starshot project in an earlier part of this journey, the proposal to accelerate a gram-scale chip to 20% of the speed of light using a ground-based laser array. But the physics of laser propulsion extends beyond that specific project in ways that are worth understanding more deeply. The key insight is that a photon, a particle of light, carries momentum. When it strikes a reflective surface, it transfers that momentum to the surface. This is radiation pressure, and it is real, it is measurable, it has been demonstrated experimentally, and it is actually used in the engineering of spacecraft today. The Japanese spacecraft Ikaros, launched in 2010, demonstrated solar sail propulsion in interplanetary space, using the pressure of sunlight on a 14-meter reflective sail to produce measurable thrust. For interstellar distances, sunlight is too weak and too diffuse to be useful, but a tightly focused laser beam is a different matter. The energy density of a focused laser can be made arbitrarily high, and a sufficiently large, sufficiently reflective sail, struck by a sufficiently powerful laser, can be accelerated to a significant fraction of the speed of light before the beam diverges too much to continue pushing effectively. The engineering constraints are severe. The sail material needs to be almost perfectly reflective, absorbing even a tiny fraction of the laser energy at those power levels would vaporize it instantly. It needs to be extraordinarily light. The lower the mass, the higher the acceleration for a given force, and it needs to maintain structural integrity during an acceleration phase that, in the breakthrough Starshot concept, lasts only a few minutes but subjects the sail to stresses unlike anything materials science has ever had to address. But here is what makes laser sail propulsion genuinely exciting. Beyond the specific breakthrough Starshot application, the physics scales. A gram-scale chip accelerated to 20% of the speed of light requires a certain laser power. A kilogram-scale payload requires more. A ton-scale payload requires much more. But the fundamental principle, using focused electromagnetic radiation to accelerate a reflective sail, is not limited to gram-scale payloads by any law of physics. It is limited by engineering, by the power of the laser array, the quality of the sail material, the precision of the beam focusing. Engineering problems, remember, have a different relationship to time than physics problems do. Physics problems can be permanently closed by a single experiment that rules out an entire class of solutions. Engineering problems just require better engineering. Now let us put all of this together in a way that is honest about the uncertainty. The Alcubierre warp drive is mathematically valid but requires either exotic energy that may not exist in usable quantities or positive energy in quantities that currently exceed anything conceivable. The wormhole is mathematically valid and connected to some of the deepest ideas in modern physics, but traversability at macroscopic scales remains undemonstrated and possibly impossible. The laser sail is physically straightforward and demonstrably real, but scaling it to human-carrying payloads requires engineering advances that are significant but not obviously impossible. None of these is a solution we can build today. None of them, except possibly the laser sail at small scale, represents a near-term prospect. But here is the thing about the physics frontier that the history of science teaches us to take seriously. The history of theoretical physics is full of mathematical structures that were derived, examined, partially understood, and then set aside as interesting but impractical, only to be revisited decades later when new mathematics or new experimental capabilities suddenly made them relevant in ways no one had anticipated. Black holes were predicted by general relativity in 1916 and widely considered to be mathematical artifacts rather than real objects for decades. We have now directly imaged one. Gravitational waves were predicted by Einstein in 1916 and considered by him to be too weak ever to detect. We detected them in 2015. The Higgs boson was theoretically predicted in 1964. We found it in 2012, 48 years later, using a machine that took 30 years to build. The universe has a consistent track record of eventually delivering what its mathematics promises, not always in the form expected, not always on the timescale hoped for, but with a reliability that the history of physics makes it hard to entirely dismiss. Whether that track record extends to warp drives and traversable wormholes, we do not know. The honest answer is, we do not know, but the honest answer is also, neither do we know that it does not. And in the space between those two uncertainties, some of the most rigorous and creative minds in theoretical physics are currently working. Not because they are dreamers ignoring the constraints, but because the constraints, examined carefully and in the right mathematical language, turn out to be less absolute than they first appeared. There is something about standing at the edge of known physics that is different from standing at the edge of known engineering. Engineering edges are defined by what we can build. Physics edges are defined by what we can imagine and then prove or disprove with mathematics and experiment. The engineering edge of interstellar travel is daunting but finite. We know roughly what needs to be built. We know what the challenges are. We know the path, even if we do not yet have the tools to walk it. The physics edge is different. It is genuinely open. We do not know what is on the other side. We do not know whether the mathematics of space-time contains solutions we have not yet found, structures we have not yet imagined, possibilities that would make the radiation and bone loss and psychological isolation problems not just solvable but irrelevant, because the journey, in the right geometry, might not take long enough for them to matter. That uncertainty is not a weakness. It is an invitation. The universe does not announce its secrets. It buries them in the mathematics, in the data, in the careful, painstaking, generation-spanning work of people who find the questions more compelling than the discomfort of not yet having the answers. And the question of whether there is a physics path through the interstellar void, a path that does not require us to solve every biological and psychological and engineering problem we have discussed, because it simply makes the crossing fast enough that those problems do not fully develop, is one of the most important open questions in science, not because the answer is known, but because it is not. There is one more dimension to this frontier that rarely gets adequate attention in discussions of interstellar travel, one that sits at the intersection of physics and biology and philosophy in a way that changes everything it touches, the nature of time, not time in the abstract, time as it is actually experienced by a body moving through space-time at significant fractions of the speed of light, special relativity, confirmed by over a century of experimental verification, baked into the GPS satellites that tell you where you are, confirmed in particle accelerators and atomic clocks on aircraft and in countless other settings, tells us something extraordinary about the relationship between velocity and time. The faster you move through space, the slower you move through time, not metaphorically, not approximately, precisely, measurably, literally. A clock moving at high velocity runs slower than a clock at rest, not because of any mechanical effect, not because of anything wrong with the clock, but because time itself passes more slowly for moving objects. This is called time dilation, and it is not a theory. It is an observed, measured, engineered for fact of the universe we actually live in, at everyday speeds, even at the speeds of the fastest aircraft or rockets we currently build. The effect is real but tiny, negligible for practical purposes. But as velocity approaches the speed of light, the effect becomes dramatic. At 90% of the speed of light, time for the moving object passes at roughly 44% of the rate it passes for a stationary observer. At 99%, time slows to about 14% of the stationary rate. At 99.9%, it is about 4.5%. What this means for interstellar travel is extraordinary. A ship traveling at 99.9% of the speed of light toward Alpha Centauri, roughly 4.2 light-years away, would, from the perspective of an observer on Earth, take about 4.2 years to arrive. But the crew of that ship would experience only about 7 weeks of elapsed time. 7 weeks, not thousands of years, not generations. 7 weeks of subjective time, while 4 years pass in the external universe at even higher fractions of the speed of light. the discrepancy grows still more extreme. A ship traveling at 99.999% of the speed of light could, in principle, cross the entire observable universe, 93 billion light-years, in a subjective time of decades. The universe at those velocities becomes navigable within a human lifetime. The catch, and it is a significant one, is getting to those velocities. The energy required to accelerate a meaningful mass to a significant fraction of the speed of light is, by conventional propulsion, prohibitive. The relativistic rocket equation, the extension of the classical Tsiolkovsky rocket equation to relativistic velocities, tells us that the fuel requirements grow exponentially with velocity. To accelerate a payload to 90% of the speed of light using a conventional rocket, the mass of fuel required would exceed the mass of the payload by factors that make the engineering essentially impossible with any chemical or even nuclear propulsion system we can currently envision. But laser sails bypass the fuel problem entirely. The energy source stays behind the laser array on Earth or in the solar system, and the payload carries no propellant. The energy required is still enormous, but it does not need to be carried, and that changes the calculation in ways that make relativistic velocities, at least for small payloads, a genuine near-term engineering goal rather than a distant fantasy. So here is where we arrive. At the end of Part 8, the physics of interstellar travel is not simply a wall, it is a landscape, an extraordinarily complex, partially mapped, mostly unexplored landscape with features that range from the definitively impossible to the definitively possible, with vast territories in between that carry the label that all great scientific frontiers carry. Unknown, the radiation is real, the bone loss is real, the psychological challenges are real, the distances are real. None of that disappears because the mathematics of space-time is interesting. But the mathematics of space-time is interesting, and it suggests, with the careful, qualified, evidence-grounded optimism that is the only kind worth having, that the universe may have more to offer than its surface hostility implies. The path to the stars may not be the path we imagined. It may be stranger, more geometric, more dependent on our understanding of the deep structure of reality than on our ability to build bigger rockets or tougher bodies. And the people who will find that path, if it exists, and if we survive long enough to look for it, will be the inheritors of every question we are asking right now. Every equation worked through, every experiment run, every night spent looking up at a sky full of unreachable light and refusing to accept that unreachable is the final answer. We have 2 parts remaining in this journey, and in the next one, we are going to bring everything together: the biology, the engineering, the psychology, the philosophy, the physics, and ask the question that sits underneath all of them, not just how long would we survive, but what would it mean for everything we are and everything we might become if we did? The answer is not what you expect, and it begins with a single, extraordinary fact about the nature of survival itself. Survival is not a passive state. We use the word as though it describes something static, a condition of simply continuing to exist, of not having died yet, of persisting in the face of whatever the universe has chosen to throw at us. But that is not what survival actually is when you examine it closely. When you trace it back to its biological roots and follow it forward through its psychological and cultural expressions into the full complexity of what it means for a conscious, reflective, meaning-making creature to endure, survival is a project, an active, continuous, resource-demanding, choice-laden project that requires not just the absence of death, but the presence of something worth living for. Something that organizes behavior around a future rather than just a present. Something that gives the energy expenditure of continued existence a direction, a shape, a reason. Every organism that has ever lived has survived by being oriented towards something: food, reproduction, safety, connection. The more complex the organism, the more complex the orientation. The more layers of meaning it requires, the more dimensions of experience it needs to sustain its engagement with the project of continuing. A human being who loses all orientation, who has no future to move toward, no meaning to anchor the effort of existing, does not simply become unhappy. They become, in a measurable, clinical, physiological sense, less viable. The link between psychological meaning and physical health is one of the most consistently documented findings in medical research. Purpose extends life, its absence shortens it. And what this means for interstellar travel, for people living inside a closed vessel, crossing a void so vast that the destination is a concept rather than a place for most of the journey, is that the survival question is not just biological. It never was. The question was always, what would they be surviving for? Viktor Frankl was a Viennese psychiatrist who survived 3 years in Nazi concentration camps, including Auschwitz. His experiences during those years and the psychological observations he made about himself, about the other prisoners around him, about who survived and who did not, and what seemed to distinguish them, formed the basis of a theoretical framework he called logotherapy, from the Greek word logos, meaning. His central finding, stated with the calm precision of a scientist who had tested his hypothesis against the most extreme conditions human beings have ever been placed in, was this: human beings can endure almost anyhow if they have a why. The physical conditions of survival, the food, the warmth, the absence of immediate lethal threat are necessary but not sufficient. What determines whether a person continues to engage with the project of survival or quietly, inexorably withdraws from it is the presence or absence of meaning, of something that makes the endurance worthwhile. He quoted Nietzsche, "He who has a why to live can bear almost any how," and he noted, with the particular precision of someone who had observed this principle operate under conditions of systematic dehumanization and extreme privation, that the why did not need to be large or abstract. It could be a person, a piece of work, a responsibility, a promise, something specific and personal and immediate that gave the effort of continuing a direction. Now think about the generation ship, the first generation. The founders, the people who chose the mission, have a why. They chose it, they understood it, they committed to it with full adult consciousness of what the commitment entailed. Their meaning is built into their departure. The act of leaving, the act of choosing to spend their finite lives in service of a crossing they will not complete, is itself a source of the kind of meaning that Frankl described as sustaining. But the second generation did not choose, and the third generation has never known Earth, and the seventh generation has only stories and records and a destination that is still, for them, a concept. A point of light in the forward viewports that looks, to an untrained eye, exactly like any other point of light. What is their why? This is not a rhetorical question. It is the central design problem of the generation ship, more fundamental than the radiation shielding, more difficult than the life support engineering, more consequential than the propulsion system. Because a ship whose inhabitants lose their why is a ship that does not arrive, not because it runs out of fuel or fails mechanically, but because it runs out of the particular human quality that is required to maintain, across centuries, the 1,000 daily choices that keep a complex system functioning. Some proposed solutions to this problem are engineering adjacent. Give the crew meaningful work, real problems to solve, real decisions to make, real consequences to manage. A generation ship whose inhabitants are passengers, whose systems are so automated that there is nothing genuinely important left for humans to do, is a generation ship whose inhabitants will find other things to do with their energy, things that may not be conducive to the mission's success. The anthropologist David Graeber spent years studying what he called bullshit jobs, Work that the people doing it privately acknowledge serves no real purpose, produces nothing of genuine value, and exists primarily to fill time and justify the social structures that surround it. His finding was that such work is not merely unsatisfying, it is actively damaging to the people who do it. It produces a particular kind of psychological corrosion that conventional measures of well-being, salary, security, working conditions do not compensate for. The lesson for mission designers is clear. The inhabitants of an interstellar vessel need to be genuinely necessary. Their decisions need to matter. Their skills need to be real skills, deployed on real problems with real stakes. The temptation to automate everything that can be automated, to reduce human error by reducing human involvement, must be balanced against the equally real risk of producing a population with no meaningful role in their own survival. There is something almost paradoxical in this. The more capable the ship's systems, the less the crew needs to do, and the less they need to do, the more fragile the psychological architecture that holds the mission together. The safest ship, from a pure engineering standpoint, might be the most dangerous one from a human standpoint. The balance point, enough automation to ensure reliability, enough genuine human agency to ensure meaning, is one of the most delicate design challenges in the entire interstellar enterprise. But there is a deeper why available to the inhabitants of a generation ship than work, or legacy, or even the abstract pull of a destination. One that emerges from the very conditions of their existence in a way that is, when you see it clearly, genuinely beautiful. They are the first, not the first humans, not the first civilization, but the first of their kind, the first community ever to have lived outside the gravitational and biological and psychological context of a stellar system, the first human beings for whom the universe is not a background or a setting but a home, the first people in the history of the species to truly inhabit the void, to wake up every morning, every ship morning, by whatever clock they have chosen, inside the dark between the stars. That is by any measure an extraordinary thing to be. The explorer and writer Apsley Cherry Garrard, who participated in Robert Falcon Scott's Antarctic expedition of 1910, one of the most brutal and ultimately tragic scientific journeys in human history, wrote in his account of the experience something that has stayed with me since I first read it. He said that exploration is the physical expression of the intellectual passion, that the desire to know what is over the next horizon, to go to the places no one has gone and return, or not return, with the knowledge of what is there is not a luxury or an eccentricity, but a fundamental expression of what human beings are. Scott's party died on the return from the South Pole. Cherry Garrard survived but carried the experience for the rest of his life. He did not describe it as a mistake. He described it as the central fact of his existence, the thing that made every subsequent experience meaningful in a way it would not otherwise have been. The inhabitants of a generation ship would carry something analogous to that. Not the grief of Cherry Garrard, not the particular weight of a journey that ended in death, but the particular gravity of being people for whom the journey was not an episode but a life, for whom the dark between the stars was not something crossed but something inhabited, something that shaped them from birth, and that they knew, in their bones, was unlike anything any human being had experienced before them. That is a why. It is not a comfortable one. It does not resolve easily into policy or engineering, but it is real and it is theirs. And it is the kind of why that Frankel's research suggests is exactly what human beings need when the how is difficult enough. Let us talk, now, about what arriving would mean, not the engineering of arrival, not the orbital mechanics or the atmospheric entry procedures or the biological challenges of readapting to planetary gravity and a real sun and an alien microbiome. We have touched on those threads already, and they are formidable. Let us talk about what it would mean. for the people aboard the ship. People who had been born into the crossing, who had grown up knowing only the interior of the vessel, whose entire experiential reality was defined by recycled air and artificial light, and the particular, intimate community of a few thousand human beings in a closed environment. The first sight of a real sky would be, in ways that are difficult to describe and perhaps impossible to fully anticipate, transformative, not just emotionally, perceptually, physiologically. Their visual systems, calibrated across years to the flat, consistent lighting of the ship's interior, would encounter direct sunlight, a different star's direct sunlight, for the first time. Their vestibular systems, adapted to whatever rotation-generated gravity the ship had provided, would encounter a gravity field that was almost certainly different in magnitude and uniformly, unfailingly, everywhere. There would be wind, there would be weather, there would be smells. If the planet had biology, there would be biological smells, the incomprehensible richness of a living ecosystem generating its volatile organic chemistry into an open atmosphere. There would be silence. Not the silence of a ship, which is never truly silent, always humming, always cycling, always producing the mechanical underlayer of continuous system operation. Real open silence, the silence of distance, the silence of a world not built by human hands, indifferent to human presence, proceeding at its own tempo. We have no vocabulary for what that experience would be like. We have approximations, accounts of solitary polar expeditions, of weeks spent in wilderness, of the particular quality of perception that emerges when the constant noise of human civilization is removed. But those approximations are earthbound. They share the same sky, the same gravity, same biological context as everything else in human experience. The arrival at a new world after a life spent in transit would be something beyond all of them. And what would it mean for the people left behind, for the civilization on Earth, if Earth still existed in recognizable form after the centuries of the crossings that had launched the mission and then waited across the unbridgeable light years for news of what happened? The signal from the ship would arrive years after the events it described. The confirmation of arrival, if the ship arrived, would reach Earth decades or centuries after the inhabitants of the ship had already lived through it, already adapted, already begun whatever kind of civilization they were building in the light of a foreign sun. There would be no shared experience, no simultaneous moment of collective celebration. The news would arrive as history, not as event, as a message from a past that the senders had already moved far beyond. There is something in this temporal disconnection that is deeply, structurally different from any previous human communication across distance. When the first European settlers in the Americas sent letters back to their families and governments, the delay was months, long enough to feel the distance, short enough to maintain some genuine continuity of relationship. When missions to Mars will eventually send communications, the delay will be between 3 and 22 minutes each way, an inconvenience but not a civilizational rupture. A signal from a ship at Alpha Centauri takes 4.2 years to arrive. A reply takes another 4.2 years to return. In the middle of the crossing, at 2 light-years distance, any exchange of messages would take 4 years minimum. By the time the mission arrived and sent its first reports, those reports would arrive on an Earth that had changed significantly in the interval. The relationship between the home civilization and the ship would not be a conversation. It would be a correspondence, slow, asynchronous, mediated by years of light-speed delay. Like letters exchanged between a medieval monastery and its parent institution, months apart, each written without knowledge of what the other had said in the interval. And yet those monastic correspondences were sustained for centuries. The relationship, however attenuated, however delayed, remained a relationship, an acknowledgement, maintained across distance and time, that the people on the other end were real, that their existence mattered, that the connection between origin and outpost was worth the effort of maintaining. The light years would not sever the human bond. They would transform it into something that required more patience and more faith to sustain than any previous form of human communication. But patience and faith are not beyond us. They are, in fact, among the things we do best when we choose to. So here is the answer to the question we began with: how long would we survive interstellar travel? The honest answer, the one that holds together everything we have covered across these 9 parts, is this: long enough. If we are serious about what it takes, the biology would be hard. The radiation accumulation, the bone density loss, the cardiovascular changes, the neuroocular syndrome, the immune dysregulation, all of it is real, documented and severe. Over a long crossing, these problems compound. They require active, continuous, sophisticated medical management. They require engineering solutions, shielding, artificial gravity, pharmacological intervention, possibly genetic modification that do not yet fully exist but that are being developed incrementally. With every mission we fly, the psychology would be harder. Isolation, monotony, the loss of natural light and open space, and the social complexity of a large civilization. These things do not kill quickly, but they corrode steadily. They require social architecture as carefully designed as the physical architecture of the ship. Communities structured for long-term cohesion rather than short-term efficiency. Roles that are real. Conflicts that have resolution mechanisms. Meaning that is genuine rather than imposed. The genetics would be different. The people who arrived would not be identical to the people who departed. Mutation, drift, adaptation, and the deliberate or accidental effects of the altered environment would make them something new. Not a degradation of humanity, but a branching of it. The first new variety of human being, created not by natural selection operating across geological time, but by a conscious civilizational choice operating across historical time. And the philosophy would be the deepest challenge of all. The willingness to think in centuries, to invest for descendants you will never meet, to commit to a project whose completion you will never witness, to board a vessel knowing it will not arrive in your lifetime or your children's lifetime or your grandchildren's lifetime, and to find in that commitment not futility but the highest expression of what human beings are capable of when they take seriously the scale of what they might become. All of this is possible. None of it is easy. Every part of it requires things we do not yet fully have: tools, knowledge, wisdom, institutional endurance, cultural readiness. But here is what I keep returning to. At the end of all this, every generation in human history has faced challenges that their predecessors could not have imagined solving. And every generation, applying the knowledge they had accumulated and the creativity they had developed, and the particular human stubbornness that refuses to accept that the horizon is a wall, has solved some of them. Not all. Not quickly. Not without cost. But enough. Always enough to push the frontier forward. Always enough to hand the next generation a world slightly larger, slightly better understood, slightly more navigable than the one they inherited. We are not the last generation. We are a middle one. Somewhere between the first humans who looked up at the night sky and felt the pull of it, and the first humans who will cross to another star and feel the pull of a different sky on the other side. Our job is not to complete the crossing. Our job is to make it more possible than it was before we arrived. The stars are not a reward for civilizations that earn them. The universe does not grade on merit. It offers what it offers, its mathematics, its physics, its extraordinary, indifferent abundance of matter and energy and time to whoever develops the tools and the wisdom and the will to make use of them. We are developing the tools. The wisdom is harder, The will, that ancient, unkillable human orientation toward what is beyond the next ridge, what is over the horizon, what is on the other side of the dark, that has never been in question. It is what we are. It is, perhaps, what the universe makes when it has enough time and the right ingredients and something to wonder about. And the stars, all those other suns burning in the dark, circled by worlds we have not yet named, under skies no human eye has yet seen, are the next question in a sequence of questions that began around a fire somewhere in Africa 300,000 years ago and has not stopped since. We will not stop now. We were never going to stop. The only question was always how far we would get before we did. And the only answer the evidence supports, the only answer the mathematics leaves open, the only answer that the long and stubborn and magnificent history of our species makes credible, is further than anyone thought. There is a photograph. You have almost certainly seen it, even if you do not immediately recognize the description. It was taken on the 14th of February 1990 by the Voyager 1 spacecraft at the request of Carl Sagan from a distance of approximately 6 billion kilometers from Earth. At that distance, our planet appears in the image as a pale blue dot, a fraction of a pixel, suspended in a beam of scattered sunlight against the absolute black of interstellar space. Sagan wrote about that photograph in words that have outlasted almost everything else written about space exploration in that era. He described Earth as a mote of dust suspended in a sunbeam. He noted that every human being who had ever lived, every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher of morality, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species had lived out their lives on that pale blue dot, on that mote of dust. He did not write it to diminish us. He wrote it to locate us, to give us, with the precision that only an honest reckoning with scale can provide, a true picture of where we stand in the architecture of the cosmos. And then, having placed us there, on that pale, vulnerable, astonishing point of light, he asked what follows from it. What our situation, understood honestly, demands of us. His answer was not despair, it was responsibility, clarity, the obligation to be kinder to one another, because there is no help coming from elsewhere, and the obligation, perhaps the deepest one, to keep asking the questions that the pale blue dot so beautifully raises. Where did we come from? What are we? Where are we going? We have spent 9 parts of this journey inside those questions. We have followed them into the biology of bodies under radiation, into the engineering of closed life support systems, into the psychology of isolation and the genetics of small populations adrift in a mutagenic environment. We have followed them into the philosophy of deep time and the physics of space-time geometry and the extraordinary, humbling possibility that the universe's own mathematics may offer roads we have not yet learned to walk. And now, at the end, I want to do something different. I want to step back from the specifics, from the sieverts and the telomere shortening and the Alcubierre metric and the generation ship ethics, and look at the whole thing, the full picture, the question beneath all the questions: why does it matter? Not in the practical sense, not in the sense of resources or territorial expansion or the insurance policy of a multiplanetary or multistellar species. Those arguments are real, and they have been made carefully by people far more qualified than I am to make them. I mean, why does it matter to us, right now, today, sitting here on a pale blue dot in the outer spiral arm of an unremarkable galaxy, watching a video about something that will not happen for centuries at the earliest? Why does the thought of it produce something in the chest? Some complicated mixture of longing and humility, and something that is not quite hope but is adjacent to it, that ordinary topics do not produce. Why do the stars do what the stars do to us? The neuroscientist and philosopher Antonio Damasio has spent decades studying the relationship between emotion and reason, arguing against a long tradition that treats them as opposites, that they are inseparable, that the capacity to reason about the future requires the emotional architecture to care about it, that the cold, logical evaluation of options is not possible in the absence of feelings that make some options matter more than others. What he describes is not a weakness in human cognition. It is the mechanism by which abstract knowledge becomes motivating, the pathway by which understanding something, truly understanding it, not just knowing the words, produces the kind of response that drives behavior. The awe produced by an honest encounter with the scale of the cosmos is not a sentimental distraction from serious thinking about interstellar travel. It is the emotional correlate of understanding what is actually at stake. It is what it feels like inside a human nervous system to genuinely comprehend that the universe is 13.8 billion years old and 93 billion light-years across, and full of hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them circled by worlds, and that one of those worlds, by a combination of physics and chemistry and biology and time, produced something capable of knowing all of that. The awe is the appropriate response. It is cognition doing its job correctly, and what it motivates, the reaching, the questioning, the refusal to accept that the horizon is the end, is not irrational. It is what creatures like us do when we are functioning as intended. When the full capacity of what evolution and culture have made us is engaged with the full scale of what the universe actually is. Let us talk about legacy, not in the sentimental sense, but in the precise one. Everything we know about the universe, we know because someone before us looked carefully and wrote down what they saw. Aristarchus of Samos proposed a heliocentric model of the solar system in the 3rd century before the Common Era, more than 1800 years before Copernicus published the same idea in a form that European astronomy was finally ready to receive. His work survived in fragments referenced by other writers, preserved imperfectly across the centuries by librarians and scholars who had no way of knowing which texts would matter. Hypatia of Alexandria taught mathematics and astronomy in the 4th century of the Common Era, in a city whose library contained the accumulated scientific knowledge of the ancient world. She was murdered by a mob. Much of what she taught was lost. What survived did so through the painstaking work of translators and copyists who carried Greek scientific texts into Arabic and eventually back into Latin, a relay race of knowledge across centuries and languages and civilizational collapses, sustained by the particular human conviction that understanding is worth preserving even when the world is hostile to it. The knowledge that now lets us calculate the distance to Alpha Centauri, model the radiation environment of interstellar space, design life support systems for closed habitats, and write papers about the Alcubierre metric, all of it is the downstream product of that relay, of 10,000 years of careful observation and honest recording and institutional preservation, carried forward by individuals who mostly did not know the full significance of what they were passing on. We are currently running a leg of that relay, the measurements we take, the models we build, the questions we ask, and the partial answers we find. These are what we hand to the next runners. Who will hand them to the next? Who will hand them to the civilization that eventually stands at the launch pad and says, "We are ready, we know enough, we are going, our job is to keep running," to not drop the baton, to hand it forward in better condition than we received it. That is what it means to be a scientific civilization at this particular moment in the history of the cosmos. Not to complete the crossing. To keep the crossing possible, there is a concept in Japanese aesthetics called mono, no aware. It is usually translated as the pathos of things, the particular, bittersweet awareness of impermanence that the Japanese tradition treats not as a source of despair, but as the foundation of a certain kind of beauty. The cherry blossom is beautiful partly because it falls. The moment is precious partly because it ends. The awareness of transience, held clearly and without flinching, deepens rather than diminishes the experience of what is present. I think about mono-no-aware when I think about the pale blue dot. We are here on this particular world for a particular window of time. The sun will eventually make this world uninhabitable. The universe will eventually make stellar civilization impossible. Every individual life ends. Every civilization ends. The cosmos itself, in whatever final state physics delivers it to, will be a place where the complexity and richness and improbable beauty of what currently exists is no longer possible. That is true. Unambiguously, irreversibly true. And yet, right now, in this window, on this dot, under this particular configuration of stars, something extraordinary is happening. Matter has organized itself into a form complex enough to know that it exists, to ask how it got here, to reach, with instruments and mathematics and the particular stubborn creativity of biological intelligence, toward the structures of the universe that produced it. Right now, somewhere on this planet, a child is looking through a telescope for the first time and seeing Saturn's rings and feeling something shift, some permanent reorientation of their internal compass toward the cosmos that will shape the rest of their life. Right now, a team of scientists is analyzing data from a space telescope and finding in the atmospheric spectrum of a distant exoplanet a chemical signature that does not quite fit the models. That requires a second look. That might possibly be something. Right now, an engineer is running simulations of a laser sail propulsion system, checking the numbers for the 100th time, looking for the error she knows must be there and not finding it. The numbers keep coming back the same. Right now, a physicist is staring at an equation that describes the interior geometry of a warp bubble and noticing something, a structure in the mathematics, that no one has noticed before. That might mean nothing. That might mean everything. All of this is happening. All of it is real, and all of it is a step, small, uncertain, imperfect, but genuine, in the direction of the stars. The question we began with, how long would we survive interstellar travel, has an answer, not a clean one, not a number you can write on a whiteboard and circle, but an answer: we would survive as long as we prepare seriously for what survival requires. As long as we solve, one by one and generation by generation, the biological and engineering and psychological problems we have spent this journey mapping. As long as we build the institutions and the cultural frameworks and the scientific knowledge and the sheer accumulated civilizational wisdom that the crossing demands. We would not survive if we went tomorrow. The radiation would accumulate faster than any current medical technology could manage. The psychological architecture of the crew would fracture under the weight of the isolation and the distance and the absence of any horizon that is not the inside of a hull. The genetic diversity of any crew we could currently imagine assembling would be insufficient for a multi-generational crossing. The propulsion systems we currently possess could not reach even the nearest star within any timescale that biology could endure. We would not survive if we stopped trying. If the civilizational investment in the science and technology and institutional endurance required for the crossing were diverted or lost, or simply abandoned because the timescale was too long and the payoff too distant for the temporal discounting of short-term thinking to leave room for it. But we would survive, we could survive, if we treated the crossing as the Cologne Cathedral of our civilization, as the project that gives the work of each generation its largest context, as the thing that we are building slowly, imperfectly, with a particular human combination of ambition and error and stubbornness and occasional brilliance, toward a completion that none of us will witness, but that all of us are contributing to. We could survive if we understood that the question is not whether it is possible. The mathematics says it is possible. The physics leaves it open. The biology, properly managed and continuously improved, does not prohibit it. The question is whether we will make it a priority that endures across the timescales it requires. That is a question about us, about what we value and what we sustain and what we are willing to invest in outcomes we will not live to see. And that question, unlike the radiation dose calculations and the warp field equations and the population genetics models, is not a question for scientists or engineers alone. It is a question for everyone. For every person who has ever looked up at a clear night sky and felt that particular, wordless pull toward the light, it is a question for you. There is one more thing I want to say before this journey ends. The stars are not waiting for us to be ready. They do not know we exist. They burn through their fuel and fuse their elements and eventually die, on timescales that make our entire civilizational history look like a single afternoon, with complete indifference to whether any creature on any of their orbiting worlds ever looked up and wondered. The universe is not cheering for us. It is not designed for us. It does not owe us a successful crossing or a habitable destination or a future in which the questions we are currently asking get answered. What it offers is something more austere and, in its own way, more extraordinary. It offers the laws of physics, the same everywhere, consistent across every galaxy we have ever observed, mathematically precise, experimentally reliable. It offers the fact that those laws allow for complexity, and that complexity, given sufficient time and the right conditions, produces life, and that life, given sufficient time and the right conditions, produces curiosity, and that curiosity, given sufficient time and the right conditions, produces the capacity to understand the laws that produced it. That recursion, matter understanding the rules of its own organization, is the most remarkable thing we know about. More remarkable than any individual discovery, any particular star or galaxy or black hole or exoplanet. The fact that the universe has produced something capable of asking what the universe is. We are that something. Improbable, fragile, brief, magnificent. And the stars, those other suns burning in the dark, are not obstacles or rewards or indifferent walls. They are the next chapter in the story that began with the first stars forming from the cooling gas of the early universe, proceeded through the deaths of those stars and the seeding of space with the elements they had forged, continued through the formation of our solar system from that seeded material, and arrived, by the extraordinary sequence of events we call natural history, at something sitting here now, knowing all of this, wanting more. The crossing to another star is not the end of that story. It is not even close to the end. It is one more step in a narrative that began before the Earth existed and will continue, if we do not fail it, long after the Earth is gone. We are the universe in the act of reaching for itself. Across the void, toward the light. How long would we survive interstellar travel? Long enough to become something the universe has never been before. Something that knows where it came from, understands what it is made of, and chooses, despite the distance, despite the radiation, despite the silence, despite every honest and sobering thing the physics and biology and psychology tell us about the difficulty of the crossing, to go anyway, to reach anyway, to ask always what is on the other side of the dark, and to go and see. And if this journey left you wanting to go deeper, there is a video on your screen waiting for you. It explores the brutal reality of living in a generation ship for 1,000 years, not the theory, the raw, uncomfortable truth of what daily life actually looks like across 10 centuries in a closed metal world. Click it, you will not regret it.